Gentlemen, if I can get my panel assembled here, we'll get started. This is the assembly of ancient dinosaurs who are looking forward to recounting their experiences over the past decade. Gentlemen, their experiences over the past decade with, wow, okay, maybe I'll stand over here and I won't do that. With the creation of the ARPANET and then the Internet that followed. And so what I hope to be able to do in this hour and a half is get these pioneers to regale you with some of their experiences, their observations, their insights, and perhaps even some speculation about where do we go from where we have now gotten with this story. My name is Vint Cerf. I'm Vice President and Chief Internet Evangelist at Google. To my left and your right is Steve Crocker, who is the CEO of Shinkuro, but he and I were graduate students at UCLA in Len Kleinrock's lab. Len is sitting right there to Steve Crocker's left. Bob Kahn is next, and David Walden. Bob was variously at MIT, Bolt, Beranek, and Newman, and DARPA, and now at the CEO of CNRI, the Corporation for National Research Initiatives. Dave Walden had most of his career at BB&N, I think, and you can correct me and add things if you like. Len Kleinrock migrated from MIT in the early 1960s to UCLA, where he has become a permanent fixture and produced an enormous number of graduates whose primary focus has been the mathematical behavior of distributed systems. So I'm going to ask Len to begin because it was his exploration of queuing models of packet switching, message switching at MIT that gave some insight into the behavior of these kinds of distributed store and forward systems. But Len, I'd like to ask if you would explain what it was that drew you to that particular problem, because it wasn't exactly on everyone's front door that they needed to understand these systems. So why did that turn out to be a topic of interest to you when you started your research?
Well, at MIT, I was surrounded by computers. And most of my classmates were working on problems regarding information theory and coding theory, really hard problems, which weren't leading in any magnificent direction. And being surrounded by computers, I recognized sooner or later they're going to have to talk to each other, and there was no effective technology which would allow that to happen. The telephone network was woefully inadequate. So I decided to create a model and try to analyze what would it be for data traffic to move in a network, and what were the issues, how could you model it, how could you analyze it, how could you optimize it. And at that time, I developed the mathematical theory of data networks. And nobody cared. There was no application. AT&T said it wouldn't work, and even if it did work, they said they wanted nothing to do with it. And you wonder why. And the reason is, when I think back, there was no data to send. There was no business model. They couldn't make any revenue on this thing called data. So the theory was developed. At the same time, at Rand Corporation, Paul Barron was doing a similar thing, looking at military networks, which would be basically robust against an attack. And this theory lay there until, as we'll discuss in a few minutes, ARPA decided they needed a network. And so the theory was waiting, the need was there, and the next step was to implement this. And I'm sure you can pick that up with the rest of the panel.
So one interesting factoid is that some of these people have been colleagues for quite a long time. Do I remember correctly, Bob, that you were at MIT when Len was there, or did you arrive after Len went to UCLA?
Len would probably have to pin it down. Probably he left before I got there, because I arrived there in roughly September of 1964, and I believe he left shortly before, but he can
I think that's right. You got to UCLA.
I left in August of '63.
Yeah. So, but MIT figures rather strongly in this picture. In particular, three of these people. David, were you at MIT as well?
I was at Lincoln Laboratory, MIT Lincoln Laboratory.
Close enough. So what you basically have here is the four horsemen of the apocalypse from MIT in one way or another. So you've done this analysis. One of your colleagues is Larry Roberts, who was at Lincoln Laboratory and was drawn by force to ARPA in the mid-1960s to go run this ARPANET project. And the motivation behind building the network was not to build a system that would, survive a nuclear attack, which is what some people misunderstand. Paul Barron was working on that problem at RAND. But what Larry Roberts was asked to do was to figure out how to build a network that would allow multiple computer science departments funded by DARPA to share their computing resources. Every one of the departments said we need a world-class computer every year to keep up their quality of their research, and even ARPA couldn't afford to buy those machines for every university. So they said, we're going to build a network and you're going to share. Larry came down to ARPA in the Information Processing Techniques Office in order to initiate that project. And that emerged as a request for quotations in 1968. And by this time, if I am remembering correctly, Bob Kahn, you left MIT and were then at BB&N. Is that correct?
If you want the exact time, maybe
no. Well, yes, I would like it, within a millisecond. But I'm trying to figure out the relationship between you and Dave Walden, who was at BB&N at the time this request came out. BB&N was one of many responders. There's a tiny irony here. Steve Crocker and I were graduate students in Len Kleinrock's laboratory, and we worked with another company that responded to the RFQ, but we lost. So you had a hand in responding to that RFQ.
Yeah, we did. But before I specifically answer that, let me just also say, Larry Roberts recently passed away, and Len organized with one of his sons a very lovely memorial service out there. Larry was a prime mover in making the ARPANET happen. I mean, I kind of view him as the mastermind of what actually happened. But absent that, Larry would be here today and probably give you the definitive view of it from DARPA perspective. From my perspective, I got involved in it sort of tangentially. I never thought I'd be involved in that project right from the get-go. When I had gone to BB&N, I'd taken a leave of absence from MIT. And the reason was I was sort of viewed both within MIT and I think even within parts of BB&N as more of a mathematical theoretician guy, sort of maybe more like Len, I guess, I don't know. But the fact of the matter is I thought taking a leave of absence made sense because I could work on a real problem rather than solving some equation or working on some theoretical things. And that's what I had understood from Jack Wozencraft, who ran the group, to be essentially getting tenure at MIT. Show that you can do something that makes a difference. And when he and I talked about what that might entail, he said, why don't you take a leave of absence for a year or two? This was not his attempt to get me out of there. He and I remained friends for a long time until he died. But go get some practical experience and come back, which is what I intended to do. And when I got there, I was working on computer nets without even knowing what DARPA was. I wasn't aware of it. And they had just gotten a DARPA contract. I think Danny Barbara was the PI on natural language communication with computers. And Danny said, fine, you want networking? Go for it. And I think part of it might have been funded out of that contract. Part of it might have been funded overhead charges. I started working on networking. And Danny's boss and my boss was a guy named Jerry Kline. And Jerry basically one day said, why don't you take that set of reports? It's like that high. Things like flow control, congestion control, all the kind of things, routing, worry about networking, and send it to DARPA, which I did. I thought maybe they'd be interested, but it never occurred to me that it would make any difference over there. It was more my development. And then I got a call back from Bob Taylor, who said, could you come down and visit? That's how I got to know who DARPA was and learned that they were planning a network. And when they finally put out that RFQ that you talked about, which was not a request for proposals, interesting. It was a request to quote on building a 4-node.
Like buying a pencil or something. As if it was an off-the-shelf item.
It was not quite off the shelf, but it landed on my desk. And I was not in a position to really a gentleman that had just been hired into BBN named Frank Hart showed up, walked into my office, and he also reported to Jerry Elkind, and he said, I understand you have this RFQ from DARPA. Can I see it? My answer was, who are you? I didn't know who he was. And one thing led to another. I ended up collaborating with him and some of the people working with him, including Dave. On actually writing the proposal to DARPA. I still have my handwritten draft of that proposal that we sent in, which was something that came to fruition by my working with another fellow in that group named Severo Ornstein, who dealt with all the hardware stuff. And eventually we put in a full-blown proposal, and it won. So that's my coupling into that group. And
you mentioned Frank Hart.
We won the award.
You mentioned Frank Hart, another one of the BB&N guys who passed away recently. But there's still a bunch of us that are left, and we're still plunging along. So, David, how did you get drawn into this thing? You were part of Frank Hart's group. Yes, David.
Well, in 1968, which is when the request for proposal came out, I was 26 years old. I'd been at BB&N for about a year and a half. BB&N's a place where they would hire people not quite knowing what they would do if they wanted them. And I had come from Lincoln Lab, and Frank Hart hired me there. So BB&N received the request for quotation according to the stamp with Jerry Elkind's stamp on August 9th. It had come out in late July. As Bob mentioned, BB&N's upper management placed the job in Frank's division, where Severo Ornstein, a hardware guy, and I, a software guy, already were in Frank Hart's group. And as Bob described, Bob came across the bridge from the other computer division, and we began to sit together. And we began to design and plan a system design for the IMP, and also an implementation plan, because we were going to make a proposal to build something. The four of us, plus a bunch of other people at BB&N, almost finished that proposal. A lot of other people kibitzing and making comments and trying to make it one that would be more readily accepted from the government. But a little while before the proposal was due, Will Crowther, another person who had been in Frank's group at Lincoln Laboratory and my mentor, we recruited him because, frankly, being not so old and with only 4 years experience, I thought we needed Will. We needed another person who was a more experienced real-time programmer. And Will helped refine the proposal. The proposal went in on September 9th. That's when it was due. It might have gone a few days earlier. And we waited. A while longer, I'm not sure how many days or weeks, we got a call to come to ARPA and answer questions about our proposal. And Bob, Frank Hart, Severo Ornstein, and Will Crowther went down to ARPA. They came back. They sounded to me like they thought they had a good meeting. And then some more time passed. My memory is, and Bob can correct me if I'm wrong, we were designing and thinking all along. We never really stopped that much, kind of informally. Before the end of the year, we were notified that we were going to get the contract, and on January 1st of 1969, we began funded work. We worked through the first 2/3 of the year, the hardware guys getting the hardware interface designs. Ben Barker had joined Severo in the hardware side of things by this time. Out to Honeywell, we were going to use a Honeywell 516 computer to fabricate the interfaces using their electronics technology. Bernie Cosell joined Will and I on the software side, and we began implementing. And of course, as you implement, you continue to design. Bob was there, and he had meetings with us and helped us think about things. By the way, I forgot to mention this. When Bob first came over from the other division, he was giving Severo and me little tutorials in networking because he'd been thinking about it already as part of our meetings. Do you remember that? It's true. So we, even though we'd never done networking before, had a real resource nearby that could help us get up to speed. We knew about real-time programming, but we didn't know about networks. So at that point, we spent the first 2/3 of the year doing the implementation. Bob spent a lot of time working with the phone company and working on documentation and in general working on the 24-bit cyclical redundancy check in general, doing whatever needed to be done. And by September, where we had a delivery date, we were able to deliver the first IMP, the first packet switch to Len Kleinrock's group at UCLA. And we delivered the next one to Stanford Research Institute, the next one to UC Santa Barbara, the next one to the University of Utah. And by early December, basically one every 3 weeks, that network was operational. There were 4 nodes now which could communicate. As each IMP had gone in, the host people would begin to try to make their interfaces work with the IMP. The user computer people made their interfaces work with the IMP. Now we had a 4-node network, which my assessment is it demonstrated, at least at a demonstration level, the efficacy of packet switching. And it also provided something where the hosts could begin to try to talk to each other and so on. A lot of people have favorite dates late in 1969 for when it all started. For instance, the UCLA meeting and the announcement for this meeting, like the day when a message was sent from UCLA to SRI. I like the date when there were 4 nodes in the field, because in my mind, that was the beginning of a revolution in research and network research and network implementation. And it certainly was the making of my career.
Well, I think everybody who's ever had anything to do with projects of this scale have different milestones that they remember, especially, and that one's yours. I do have to remind you of a story. When BB&N won this contract, they got a message from Senator Ted Kennedy congratulating them on their ecumenical effort, because he had misunderstood that what they were building was an interfaith message processor instead of an interface message processor. So there was a reason that the first packet switch was sent to UCLA, and that's the reason is sitting right over here, Len Kleinrock. So can you say a little bit about what it was about your job or your work at UCLA that caused the first node to show up there?
Sure. And in answering that, I can fill in a little bit of the pieces that came up in the rest of this discussion. MIT Lincoln Laboratory is mentioned. They played an essential role both in my education. They sent me to MIT. They sent Larry Roberts to MIT on a full scholarship. And we were office mates, Larry and I. And that's where Larry began to see a lot of the work I was doing on networking. There was a lot of sharing among the PhD students. And Frank Hart came out of Lincoln Lab. Lincoln Lab provided a lot of the talent that eventually gave rise to the ARPANET. So you think about this proposal that was sent out, or this request for quotation, and how was it generated? When Larry came to ARPA, unwillingly, as you suggested, he was dragged there, and happily he was, we had to put together a specification as to what this thing was we were going to ask for a quotation on. And so a bunch of us got together and started laying out what this would be. For example, they wanted the system to appear like a time-sharing system to the users at any node. And the point was made, if it can't respond in half a second, this is not a good enough network. So the spec was put in that the response time for short messages should be no more than half a second in the spec. Question is, should be reliable. Well, to make it reliable, you could play the game that ATT did and said, it'll be 99.999959's reliability, which is immeasurable. There's various definitions as to what that means, but it's not practical. We decided it should be such that if any node or any line fails, everybody else can communicate. That's called a two-connected topology. It's a very practical and theoretically provable capability. It was put in. And when I was there and I said, look, if we're building an experimental network, we better build in measurement tools. This is an experiment. Be able to test a network, generate traffic, collect the traffic, trace packets, etc. So that software for making measurements and pushing things through the network was built in as part of the spec as well. So now to answer your question, what I just described is why UCLA was chosen to be the first node of the ARPANET. It's because we had the tools available to test the network, understand the theory, make models, anticipate what should happen, and then prove experimentally that it did or did not. And if not, why not? So UCLA was chosen to become the network measurement center of this evolving and emerging ARPANET.
So it turns out that I mentioned earlier, Steve and I were graduate students working for Len in his laboratory. And Steve ended up being the founder of what is now called, or was the Network Working Group. This is just an informal collection of graduate students at many of the different universities, all to become part of this ARPANET. And he has the problem of trying to figure out how to get all the host computers that connect to this homogeneous network to interact with each other. So my recollection is that you were hoping that the machine that they were sending from BB&N would be delayed because it was the Labor Day weekend and they air-shipped it instead. Would you like to just expand a little bit on your role in all of this?
Yeah, you bring back vivid memories. BBN was a very organized professional group, and those of us who were distributed around at the various sites were considerably less so. First IMP was coming to UCLA, and we were feverishly trying to get our software on our Xerox Data Systems Sigma 7 computer working.
Number 4 off the production line. It was a brand new machine from a company that was very new.
Used to be SDS, and then Xerox bought them and so forth. Right. And we had to get we had to design a hardware interface, and Mike Wingfield did a super job on that. Meanwhile, trying to get some software working was slower. We heard that BBN was having some timing troubles, and I thought, oh goody, that means that they'll be late shipping their machine. They fixed their hardware, their timing troubles. They put the machine on an airplane, and it showed up about 2 days early before the 1st of September. And my estimate of 2 weeks grace disappeared, and there was some pressure. I want to pick up on that thread and both open the scope a little bit and pick up on some points that you said, Len and Vint. You made reference to we had all these machines at MIT, and you could see that they're going to be connected together. And ARPA, originally the agency was named ARPA, and then it became DARPA, and then it became ARPA again, and now it became DARPA again, had within it, as a funding agency in the Department of Defense, had within it this office called Information Processing Techniques Office. And if we roll back time a bit before the 1968 RFQ into the sort of mid-60s, 65, 66 timeframe, the same perception that you alluded to, Len, was also quite visible and evident in this office. That office was funding advanced computer science research, and the idea of computer science research was not yet a clear-cut idea within the academic community. National Science Foundation was putting computers into universities primarily to support hard sciences, physical sciences, to do large-scale calculations. You had major computer centers. Computers were very expensive, and so there was a question of how to pay for them and how to meter out the time. And hence, the mode of use was batch processing. But in certain areas, and particularly in the areas that were supported by this office, by IPTO, interactive computing and the development of time-shared computers was far in advance of what was around in the rest of the community. And as a consequence of that, it was very visible that you had communities of people who were interacting, and two or three things were evident all at once. One was that interaction was much more productive in terms of human time, even if it was less efficient in the use of the computer. Another is that it created communities that could interact with each other. If you have 30 or 50 people who are using the same facility, it creates a natural community. And then the idea of interconnecting these computers so that you not only could get the resource sharing, which was alluded to, which might be more efficient, but you could also get collaboration. You could get collaboration on the people dimension. People interact with each other. And you might have different facilities available on one machine or another, and you might be able to gang those together in ways that would give you novel computing. So all of those ideas were in the air. And it was that which was driving the idea that we should connect these computers together. Then that leads into, well, how are we going to do it? And the work that Len had done, the work that Larry Roberts had done, became very important. And Larry Roberts was recruited to come down to ARPA to make this happen. But the precursor of all that was this vision and determination. And there had actually been some earlier experiments trying to gang a couple of computers together, hook them up with intermediate results, some positive, some negative. And Bob Taylor, who was Larry Roberts' predecessor in IPTO, decided that the time had come to try to have this network which would connect the different research sites together, not solely for the purpose of experimenting with packet switching. And in fact, one could argue that the focus on packet switching was subordinate, or subsequent in any ways, to the initial motivation, which was we needed to get the people to work together, we needed to get the computers to communicate, and we wanted to have a way to do that. So that layer, if you will, of we're going to have computers connected to each other and the people connected to each other, was the driving force. You've heard a lot from Len and from Bob and from Dave about then the details of getting the groups together, developing the software, developing the hardware for the routers, which were called the interface message processor, or IMPs in those days. But at the end of the day, the question was, what are we going to do with this network? Yes, we have to build it. Yes, we have to test it. Yes, we have to measure it. Yes, we have to understand those dynamics. But you get all that to work, and what are you going to do with it? So one of the strategies that IPTO used, that Larry Roberts used, was to implant this network in the research community that was already being funded. So we had a series of computer science research places: MIT, UCLA, Carnegie Mellon University, Berkeley, Harvard, others, Stanford, and they were gifted this network, some more happily than others. Some felt that this was an intrusion in their carefully built up structure and weren't initially too thrilled with the idea that there would be others from the outside using their facilities, but others very happily interested in the ideas and the new technology. As you've heard, UCLA was selected as the first site, and SRI, Santa Barbara, UCSB, and Utah were the next three sites. And it then became a natural issue of, well, okay, this is coming. The RFQ is out. BBN had got selected. They're going to build this thing, and it's going to arrive on our doorsteps. And Vint and I were at UCLA, and so we had to deal with what are we going to do with this. We met representatives from the other 3 sites almost simultaneously with the RFQ hitting the street in August, and we began to form a loose, very informal and unchartered coalition to think about what are the host computers, the computers that we were using for our research, what are they going to say to each other? Taking the IMPS and the subnet that BBN was building, hadn't been selected, BBN hadn't been selected yet, but the rough outline was clear. What are we going to do with this network? And so we chatted with each other intermittently. We met every few weeks, and we generated an informal set of notes eventually, trying to figure out from a clean sheet of paper what would be the architecture of the protocols that we would use to do that. And from those very tentative first steps, some structures started to emerge, and the structures were a combination of technical structures, protocol architecture, and a kind of social structure of how to work with each other, how to communicate, and what the process would be for arriving at conclusions with that. And I'll subside at this point, and Vint, you can easily pick things up from there.
Bob?
I would just like to elaborate on that a little bit. See, not everything was quite as smooth and straightforward as you might expect. In the early days of trying to get this network up and built, we did something back then, or DARPA did, to be specific, that would be very hard to do today. What Steve described as computer resource sharing was really the mantra of what this was all about. People kind of sort of intrinsically thought that if computers could interact with computers, a small set initially of people and machines and maybe a larger set later, that good things could happen. Today, some 50 years after we've started that, we still haven't achieved, I believe, even a small fraction of what people were thinking might be possible. We did some simple things at first, use the net to replace wires, more economical. But we're doing things that you could have done before, maybe at lower speed, maybe with more errors and the like. But even today, it's still a dream in the future. Today, if you put something like that on the books of one of the major funding agencies, you couldn't explain what you were going to do with it. What problem was it solving? I don't think you could fund it today. So that was one of the interesting conundrums from back then. The second thing is that even building this network, even though we got all kinds of people to work together, was by no means a straightforward and simple thing. And I think it's important in understanding history to know what things are just sort of engineering things where you kind of lay out the plan and you do it. Len described, what the inputs were to DARPA. And when the RFQ came out, they actually had some fairly high-level inputs. Half-second delay, reliable computing, all of that sort of stuff. But, if you were to compare it with, let's say, Kennedy and the moonshot, he had those kind of descriptions in the plan for going to the moon. Take a person there, getting back safely to the Earth, payload of enough to at least get a person there, maybe some other stuff. But it didn't say, how you would do it in detail, how to build the rockets, how to build the control systems. We knew in the early days that, the network would potentially be useful for the DoD if you could do it. Otherwise, DARPA never would have funded it in the first place. And Paul Barron had written some very interesting articles about what he called message address box switching. But that was before there were computers around that were practical to use. He was talking about hot potato routing from AM radio stations around the country. It wasn't really a viable net. No carrier would have ever done anything like that, and it was all sort of hypothetically, in case we were ever attacked in a nuclear scenario. We were all worried about thermonuclear war back in those days, at least at the RAND Corporation. So it was a very challenging and interesting time. the task that BB&N had was literally to do the design task initially, as Dave said, and then to actually build it. And the design task was not even a simple one. I'll give you 2 examples. One, in developing the network concept initially, we had a lot of discussions. Dave was part of it. Many people at BB&N. Should we make these nodes with hard disks, which is what DARPA was sort of expecting, so you could store a lot of packets? And we pushed back very strongly and said, no, don't do that. There's latency to store it. You know, who wants to build all of this storage inside the net? Push back and stop it at the source. So there was a set of discussions about that, and I think our proposal to literally do it in core memory was, in fact, the right one. Second one was even more controversial. There was a very interesting book that was written by Katie Hefner called Where Wizards Stay Up Late. It's great reading. I loved it. And Katie is a great writer. But she wrote an initial version of that, which I got to see very late in the game. And it had a whole description about the very issue of congestion in the net that I looked at that and said, Katie, that's just not right. And where did you get that? She said, well, that's what I understand happened. And I said, you know, in 1972 or 3, early 73, when we went out to do the testing, Dave and I went out to
70. It was early.
70. That was 1970.
No, 1970. We went to UCLA.
That's right.
This
It
is when
was
you and I got
1970.
Yeah, and Vint was there too.
Yeah, 2 years before. 1970, we went out to test it.
Yeah.
And the thing we set out to do initially was to show that the way the network was currently implemented had the potential for locking up.
Yeah.
And we did it in 12 packets.
Yeah.
Dave had it in his little
But if
book
I could
there.
just say a word, Bob had been talking to us about some of these things during the implementation in 1969, but we were very focused on getting something fielded, and we weren't listening too hard, frankly.
That's the first time you've ever said that.
I have said it before many times. And once the 4 nodes were installed, then we were able to hear. And in fact, we went out to test. Bob can say more about that. But an important point is we had an initial demonstration, but we spent the next several years correcting algorithms.
Yes, you did.
Replacing algorithms that didn't work so well, replacing algorithms that work pretty well but not at high load, and so on. So the underlying IMP project was an ongoing job in parallel with the hosts all getting up, and from my view, it worked really well. You know, we communicated back and forth. You know, when the big bug was found that Bob pointed out, and it locked up, I sent a message out to the host saying, please don't do that until we get it fixed. And they didn't do it.
So just to fill in the one more detail here. In, 1968, I get my dates right, while I was still thinking about networking, I thought it would be really nice to have a simulation program to test various algorithms. And I worked with a fellow named Warren Titleman, who had been one of the implementers of something called BBN Lisp, which later morphed into InterLisp, to write a graphics simulation program. It ran off of the BBN machine. They had a pager. It was a time when people weren't doing graphics on time-sharing systems. They mainly had Model 33 teletypes. They were printing things out, just character strings. And we actually built a really lovely simulator. So you could say, when the packet is at this node, apply these algorithms. And it was all done at a very high level in Lisp. And he had to create a display version of Lisp to do that. And then the fellow I was working for was Jerry Elkind, had funded the work on that. But when we won the contract, Jerry came to me and he said, if you want to work on networking, you're going to have to get the money from Frank, because the contract was there. You didn't want to take it out of any of the other contracts. And so I had a decision to make, because Frank had basically said, we're not going to worry about the things that you worry about. It was what Dave was just referring to.
Yeah.
And not listening about congestion and the like. His argument was like, packets are not going to congest. We won't get deadlocks. It's like, should people in this room worry if all the oxygen molecules were to show up in the corner of the room over there and we'd all suffocate? It's not going to happen. It doesn't happen. And besides which, if it ever did, we could go back and fix it and maybe put in a fan or equivalent. And so it got left out. And to me, that was a real frustration. So when Dave and I went out, that was the first thing I set out to do. When Katie wrote her book, she described it this way in the first version. It didn't show up in the final version of the book. What she said was, Dave and I went out and we discovered when we were out there that the network could lock up.
It's the other way around.
She described exactly the inverse, like we had no
We confirmed Bob's belief.
Yeah. So, and I couldn't convince her at the time that she had it exactly backwards. And I said, there's no proof that you ever even did that. I said, yes, there is. And I pointed to a paper that Warren and I wrote describing that display program, which was in a public conference. The publication was at Princeton University in mid-'69. So when she looked at that, she said, I guess I can't resolve it. And she literally deleted that whole part of the book. So it doesn't show up
I've got
anymore.
two hands up over here. Actually, which one, Len, I don't know what either of you are going to say, so I don't know which is closest to the
We're
topic.
not sure either, however.
All right, go ahead.
Picking up on what Bob said, I had written a simulator in 1962, which was a graphic simulator with light pen and all the rest and moving cues. But the object was actually to worry about something different, which at the time was not clear. If you had an uncontrolled network with these packets and messages flying around, would the thing settle down? Never mind lockup, which was another kind of issue. Did this thing even work? And the simulator was able to show, as well as the theory, that it would work. The second thing I want to point out to is something that both Steve and now Bob has referred to, and I think you did, Vint. This idea, how did all this wonderful work take place, this magic? What was it about that period? And it started with the culture at ARPA of how they funded these projects. They would go to a researcher and say, you're a great researcher. Here's a pile of money for a long period of time. Do something in which you're expert. Shoot high. Failure's okay. We're not going to watch you. Go ahead and do it. Now, with that kind of enablement, great things did happen. And in fact, the idea that Steve was talking about, the idea of sharing computer resources, was in fact the underlying idea of sharing communications resources out of the time-sharing world. In fact, the early internet, the ARPANET, was the first of the shared economy systems, which we now call Uber and Airbnb, etc., sharing things when someone else is not using it. But continuing with this philosophy, this funding culture, when the PIs got that money, what did they do with it? They went to the graduate students and said, look, we got a problem to solve. Go solve it. We're not going to tell you how to do it. Try. Failure's okay. Shoot high. Run with it. And in fact, that permeated, and then they started forming these groups, and it was wonderful the way it picked up. But as Bob says now, that kind of capability is just not there. There are too many restrictions, confinements on how funding is done. But in those days, it was enabling, and it was unbelievably productive.
Steve?
I'm going to shy away from the funding issues for a second, but an anecdote related to the store and forward lockup issues and the congestion control. So you've heard about the design process in 68 and 69, the testing and measurement that Bob and Dave did when they came out to UCLA in the early part of 1970. In mid-1971, I interrupted my graduate studies at UCLA and joined the office in Washington and in Virginia
the ARPA.
at ARPA. And I had been very active in helping in the design process for the host software, and also in providing specific advice to individual sites on how to write the software in their hosts to connect up to the ARPANET, and in organizing others to help do the same. So I arrived reported to work in July 1971, and 10 days later, my boss, Larry Roberts, sent me down to Oklahoma City to interact with some Air Force people at Tinker Air Force Base. He had arranged that 10 days later, my boss, Larry Roberts, sent me down to Oklahoma City to interact with some Air Force people at Tinker Air Force Base. He had arranged that they were going to run a side-by-side test comparing the ARPANET to the existing military communication system called Autoden. And the folks at Tinker Air Force Base were going to get an IMP, and they were going to connect one of their computers to an IMP there, and there was going to be another one at McClellan Air Force Base outside Sacramento. And I was supposed to advise them on how to write the software that they needed to do. So I recognized that the desirable thing was that we wanted to make the ARPANET look good, and so we wanted the maximum throughput. There had been a regimen related to the comment that Dave Walden just said about don't do this, of limiting how much you send in a particular conversation. I was not tuned into it because my primary attention was I was more focused on artificial intelligence and other things. And so I advised these guys that they should open up several parallel connections and throw as much data forward as they could, and that would make it all look good. So they listened. They were very sharp Air Force captains who were also graduate students at Texas A&M, as it turned out. And over the next several months, with a couple of visits, they eventually got their software up and running. I was in a meeting at MIT in a closed conference room, and I got tapped on the shoulder that there was a phone call for me. And it turned out that these guys had turned on their software in February of 1972 now, and 4 seconds later, the entire ARPANET crashed.
I ended up with a notebook full of stuff from Tinker and McClellan, because I was the guy who was writing the software in our host machine at UCLA to actually capture a lot of that measurement stuff. And I don't know what happened to that notebook. I got to continue this a little bit.
I'm sorry.
A little bit.
So I was pulled out of this meeting, and I picked up the telephone, and there was a colleague from BBN, Severo Ornstein, yelling his head off. "Why'd you do that?" And I said, "Hi, Severo, what's up?" And eventually, as he calmed down, I got the picture of what happened. And he said, "You did this on purpose." I said, "Well, not really." He said, "They said you smiled when you said it." I said, "Well, yes, I thought it was a clever idea." And he's still yelling at me. I said, "You know, Severo, I'm a civil servant. This is really more my network than it is yours." So we got past that. But the issue of what do you do with overload and congestion, and particularly these routers, these IMPs, had a limited amount of memory. Memory was very dear in those days, and so buffer space was a very useful, precious, resource. And how to manage that and get it just right was one of the big challenges. They obviously got past that, and the network continued to operate.
Well, the problem was we were making measurements at UCLA, and measurement messages happened to be 2 packets long, which requires a process called reassembly. And at that time, the storage had been doubled, pointers were not allocated, there was a hardware misjudgment. And every time we turned on measurements, the network went down. These guys yelled at us. They fixed it. We turned on the measurements again, took it down. They yelled at us a second time. And finally, we figured out what the trouble was. There were lack of pointers, et cetera. But we had a lot of fun back and forth.
We did.
Breaking, fixing, breaking, please fix. Fix it quickly. Anyway, that was the iteration.
There were 2 things I wanted to mention. One is that clearly for the DARPA project, this was important so that you could at least get reliable and affiliate with low-cost communications. But the thing that made packet switching visible in the public space was a demonstration that we put on. I was asked to put it on by Larry Roberts originally Steve actually doesn't recall, but he called me later and said, Larry wants to do it at the Washington Hilton at the ICCC event. So we did that, and it was a kind of a week-long event with everybody who is anybody in the networking field showing up there for a week, housed in the ballroom there. We had an imp in the center of the ballroom. We had a lot of terminals around and computers all over the country. There were roughly 40 of them or so at that time. And you could sort of see what it was all about. We had a contingent from some of the commercial folks there, didn't quite believe it, but it really put it on the map as a viable technology. Many years before, they were writing about how this was kind of radical, it would never work. We heard people proclaiming packet switching didn't obey good data principles, whatever those were, but you'd hear things like that all over the place. The second thing is the implication that it had for DoD. Remember, the funding came from a DoD budget, and DoD was very interested in communications, but they had invested in something called Autodin 1 for communications way back, and Autodin 1 was a kind of a message transport system which involved tapes. Very slow, and they wanted to build a new system. They came up with something called Autodin 2. It had been proposed out of the Defense Communications Agency at the time, and it was their first proposal was to build a fast circuit switching system, which had all kinds of issues when speeds went up enough as to whether it was the right long-term choice and whether it was really a good choice for computers at all. And that ended up in a dialogue between DCA and their supervisory body in the Pentagon, which was, I think, C-Cubed-I or DTAX or ASA, one of those names, C-Cubed-I, I think, at the time. There was a report commissioned by C-Cubed-I, and maybe it was commissioned by DCA, but it was asked for by C-Cubed-I, and they gave it to Lincoln Labs. And so Lincoln Labs wrote a report. It was essentially honchoed by a guy named Erwin Lebo, who later became the chief scientist at DCA, and it basically said, why don't you build a thin line system based on ARPA's packet switching technology rather than spending a lot of money, and just let that be just demonstrate whether it can work, and if so, use it. You don't need to spend that. It was rejected inside of the Defense Department because how could a bunch of researchers know how to build a real military system? And so they didn't go that path. They put out a bid. The contract was awarded to build an Autodin 2 system based on packet switching. So it had the effect of changing the mentality in DCA, which was not a trivial accomplishment. And they awarded a contract that eventually they spent, I think, more than $100 million building. The decision-making that led to that was kind of interesting, and I was then asked in my DARPA role by Lee Pascal, who was then the director of DCA, I think a 3-star general, if I would lead a blue ribbon panel to evaluate the inputs that they got. And I remember after we did that, and I met with him, I said, I have 2 topics that I'd like to talk to you about, but I don't know if you want to hear about both of them. And he said, what are they? I said, one is whether you should have done this procurement in the first place, and number 2, about the comments that you got on all the proposals. He says, I don't want to hear about the first, because it's already been out there. The reason we did it is because I'm trying to deal with the people here who have their own set of needs and requirements, and this was to address them. I don't want to hear that. So we then commented on the specific proposals that came in. He listened very carefully. They let the contract out, and the party that won it thought they'd build it and then they'd have maintenance requirements going forward. At the end of that contract, the DoD accepted the system that they built, which involved, I think, 8 hubs, each of which was staffed by 8 people times 3 shifts. So they had a lot of people. It was very expensive. It was about 1/10 the throughput of the ARPANET and probably many times the cost. They canceled it one day later, and they went back to essentially what was Erwin Lebo's original proposal. So it had a big effect on defense, not only in terms of what they did, but how they got there. So, I mean, it was a major DARPA contribution that really changed the way DoD works. And today, that defense data network is still in operation.
So I want to come back to something, if I could, because we're going to run out of time. This is to take you back to the gestation of some of this work. We've already alluded to the fact that the resource sharing motivation came from a belief that computers could do more than simply compute numbers. So J.C.R. Licklider at MIT, who was the first IPTO director, was a psychologist who had an inherent belief that computers could augment the ability of human beings, and he had found a kindred soul in Doug Engelbart at SRI International, who had a similar view that human intellect could be augmented by the use of computers doing non-numerical kinds of computation. So the second node of the ARPANET was SRI International, and the place where it landed was in Doug Engelbart's Augmentation Research Center. And that takes us to the headline of this session, because that was the second node that went up. Before that node was in place, the IMP couldn't talk to anything but itself. I mean, we were able to make packets flow from our Sigma 7 machine back into itself, but that was not a very exciting network, to be honest. So the first time that the two nodes of the network could be used to connect the two hosts that were in place at SRI and UCLA was on October 29th, 1969. And so Len had one of his students, Charlie Kline, doing a test. It was Bill Duvall, who was up at SRI International.
I think so.
Yes, yes.
And so what happened, Len?
So as Vint described, we now had a two-node network. One node does not make a network, but two does. And as Steve had said earlier, the idea was to be able to use someone else's machine as if you were local to that machine. So you sit at one node, you log on through the network to a second node and use the resources at that node as if you're a local user. Two nodes, let's try it. So Charlie Kline, we were down there in our computer room, we were going to try to log in from UCLA through the network to the SRI host. All we wanted to do was log in. And to make sure this worked now, Charlie was down at our location. I was there with him. And Bill Duvall was up at SRI. Now we're going to try this new thing called packet switching. We have no idea if it's going to work. We hoped it did. So to be sure, we had a telephone connection between Charlie and Bill. Now look at the irony here. We're using a telephone connection to prove a technology which is going to eat the lunch of the telephone network. And eventually it did. So all we want to do is log in. Now to log in, you have to type L-O-G, and the remote machine is smart enough to know what you're doing. It types the IN field. So all you have to do is type L-O-G. So we're prepared to make this monumental test. Now let's compare it to history. The first telegraph message. What did Samuel Morse prepare? What hath God wrought? A good message. How about Alexander Graham Bell? Come here, Watson, I need you. Neil Armstrong, a giant leap for mankind. Those guys were smart. They understood public relations. They understood media. They had the press, a camera, and all the rest. We didn't have a camera. We didn't have a sound recorder. We just had two guys, telephone, make a connection. So Charlie types the L. He says to Bill, you get the L? Yep, got the L. Get the O? Got the O. Get the G? Crash. Network went down after LO. So, two comments. First of all, what was the first message ever on this network? Lo, as in, lo and behold. We added that later. But it was the most prophetic, most profound, most succinct message we could have asked for, and nobody knows it. Hopefully the title of this session will help spread the word. But it was a very effective message. Now, the question is, what broke? Why did it fail? Well, it wasn't our Sigma 7, and it wasn't our IMP, and it wasn't the first piece of the backbone network line from UCLA to SRI, and it wasn't the SRI IMP, it was the SRI host. So it was their fault, it wasn't ours. And we can tell you why it failed, but the first message ever was low. September.
So, Vint, can I ask Lynn a question? Is that appropriate? So we spent, 2 years or thereabouts after that trying to develop protocols to embed in the operating systems to actually make the network work? Yeah. What protocols were you using back then?
We were just none at all. We were basically acting there was a host IM protocol at the time, and an IM protocol, and we were just trying to log in locally to that machine. That SRI machine didn't know we were coming into the network.
It was an ad hoc lash up of a kind of just telnet-like. So at UCLA it was the client side, which was easy, and then SRI had the stronger burden of having the service side, and they had added software to their operating system to bring the network messages in and treat them as if they were dial-up messages. Mm-hmm. And the glitch was that their operating system, which was very smart, as Len said, would fire back GIN after it saw the LO and the G. But the software that they had added for the purpose of running this little test was not expecting more than one character in response to a character typed in.
So it was a 10X machine at SRI.
It was an SDS 940.
940?
It was an SDS 940 there.
Yeah.
Running, okay.
But it had some very sophisticated programmers. Jeff Rulison was a crackerjack, and Bill Duvall and others. And it was just a relatively minor thing, but it creates a nice anecdote that make a full meal out of here.
So I want to come back to origins for just a second, because none of this, I think, would have happened if it weren't for the fact that computing was getting less expensive. And machines used to be batch-oriented machines. You submitted your big deck of cards, and 24 hours later you might get something back. Time sharing arises at MIT around 1961 or so with John McCarthy and some of his colleagues, Corbato, I guess, and some of the others. McCarthy brought that idea to Stanford University about the time that you went to UCLA. He came to Stanford. But this idea of sharing the machine and making it look like you had a machine all to yourself, but it was actually time sharing, turned out to be one of the key reasons why this whole project made any sense at all, because it meant that multiple parties scattered around the network could be accessing the resources of any one of the institutions concurrently. And so the time-sharing notion was part and parcel of motivation for building the network and making it interactive. And I think that, once again, is another example of timeliness of some of the technologies that came together to make this project useful. So I think I want to spend some time, we have a little here, I want to spend some time with Steve now, because Steve's work at the host level took us into territory that no one had ever been in before, which is trying to get machines of different brands to talk to each other. These machines had very different characteristics. Some had 16-bit words, 32-bit words, 36-bit words. So Steve led the network working group to develop the host level protocols. And I don't know whether you want to comment at all on what you learned from that, but I know that it had a big influence on the architecture and design of the Internet protocols later.
Well, thank you. So that's exactly right. As I said earlier, those of us who were at the different sites started to talk to each other, and without a grand plan, started to tackle the problem of what should our hosts say to each other. We knew, of course, that there were two functions that were very obvious. We'd want to be able to remotely log into a remote machine, and we'd also want to be able to move a file wholesale from one machine to another. We had some brief discussion about email, and we thought it was pretty low-key and uninteresting, too simple in a way. It, of course, took over everything until the World Wide Web became even bigger. But right from the beginning conversations, we had in mind that we didn't want to underplay the structure. We wanted to provide building blocks that you could do things that were not necessarily yet envisioned, but would leave room for others to build on. And so we, as we met, and we kind of self-organized. A few people from each of the sites started to interact, and first decision we made was to visit each other's sites and get to know each other better. And we knew that that simple decision was running counter to the whole idea of a network which would make it possible to collaborate without busting your travel budgets. And the first thing we did was bust everybody's travel budget. Yes. Len had to go get some more money just so I could go traveling around. I was very proud of that, actually. So we looked for a framework for these protocols. I don't think what we did was spectacularly clever or elegant. We tried, and there's certain parts that I could go on at length about. Dave Walden and his colleague Will Crowther at BBN were working very focused on getting the underlying network working, but they watched what we were doing and sent some critical comments at one point, and I said, yes, well, okay, and then we just proceeded straight down the path we were on. The really important part of all that, however, is that as the ARPANET morphed into or became the seed that led to the Internet, and I want to come back to that in just a second, and then Vint, I'm sure, will say a lot more about it. But the idea of these protocols sort of existed on their own at a level above the basic packet switching substrate that or subnet that was being built, and created a structure that persisted and expanded rather elaborately over, what now, 50 years.
5 decades, that's right.
Amazingly so. And so there are protocol designs. And how many protocols are there? It turns out to be a large number of protocols, more than one would guess. I heard a deputy director at NSA describe going into federal court and trying to get a warrant and saying all the things that they had to measure and all the things they had to probe, and the judge is asking very pointed questions. Well, how many protocols are there? and giving him a hard time. And he describes, well, they had to go away and they had to count them, and they came up with 100+ protocols, and they came back with a very precise number. And then a short time later, they had to go back for another meeting with the judge on another warrant, and they knew that they had to come up with the precise number, and they said a different number. And the judge said, well, how'd that happen? Why are there so many more protocols now than there were before? It's a very active process. And what the judge said was, who let that happen, actually? But there is the sort of ground-up process, bottoms-up process of creating protocols. So you have host-host protocol, you have the telnet, and you have TCP and IP and HTTP and email protocols and DNS and so forth. And those are just the most visible of what are really hundreds of protocols that do a variety of different things. And what's critical is that there's a process that is very active. The Internet Engineering Task Force continues to roll along after multiple decades and meets 3 times a year physically and has 100+ working groups all of the time. And that developed a life of its own. And at the same time, the ARPANET triggered a intense desire for other networks and consequently the need to interconnect those other networks. And that, and I'm going to intrude in your space a little bit, but that need to interconnect networks was really threefold. There were other technologies developed within IPTO, packet radio technology and packet satellite technology. So even within one funding agency, even within one office, the need to interconnect these disparate kinds of networks. Then you had within the U.S., you had different agencies. You had NASA and Department of Energy, for example, and NSF, all of which wanted to build networks and a recognition that these need to be connected. And then, of course, from a global perspective, you had countries. At UCLA, while us graduate students were just sort of wrestling with what do we do, we were visited by the Canadians and the French and the British, and it was evident that it became a national priority. We too have to have a network. So you had this push to interconnect networks and to make a very long, complicated, and probably thrilling in the end story. The internet emerged out of that. Vint will make much more sense out of all that. But the point I want to make is that you had, from this ARPANET development process, you had not only the proof that packet switching was efficient and could be made to work and be made to work reliably and so forth. But you also had this protocol layer on top of that persisted and became a life of its own. And then on the packet switching level, you had the creation of multiple networks and a need to have these different packet switching networks interact with each other, even though each one of them was under its own administration.
So it didn't actually have to be that way, though. Bob will remember that certain different kinds of transmission systems were incorporated into the ARPANET itself. In particular, there was a dedicated satellite hop that connected the ARPANET from the US all the way into Norway and to London. And it was possible to have incorporated mobile radio, for example, into the same architecture. But Bob had a different idea about that. And so maybe you could tell us why you saw the value in breaking out the different communications media into distinct networks instead of trying to incorporate it all into one.
Well, the thing you're alluding to, I'll talk about explicitly, but let me say part of the more general notion was that if the networking capability was to expand around the globe, it couldn't go the way DARPA had originally formulated it. And, Larry Roberts was much more modest than most people probably realize, because he played a very important role in getting the ARPANET going and sort of masterminding that whole thing. But, when I think it was Vint, you, Len, myself, and Larry got the Draper Prize back some number of years ago when they had a session after the fact at Draper Labs. And Larry got up and he made a comment that I thought was pretty amazing. He said, he always knew this technology would be important. He said, but the path that they were on never would have gotten it anywhere, except for the fact that the protocols that we came up with were what enabled different administrations and different people to build it independently. So he graciously gave a very nice compliment to the work that was done on those protocols at that time. But so that was one phase of it that I saw. Number two was that I was pretty convinced that we needed something beyond the NCP protocol if we were ever to get into the wireless area, mainly because you could get lost packets and the like, mainly because you could be behind tunnels or in tunnels behind mountains and the like. So that was another one. And then there was a specific instance that we ran into, which was trying to extend the ARPANET over to Europe. So the first link was a dedicated link from actually Etam, West Virginia, to Tanum, Sweden, to connect to a Norwegian seismic array effort. And then we managed to convince the combination of NTA, which was the Norwegian administration, and the British Post Office to build a link down to London. And so they paid for that, a 9.6 kilobit line. And then from there, Larry had made some arrangement to build a 2.4 kilobit link to Stuttgart in Germany, where the European Command Center was. And that was almost the showstopper that broke it, because the way European rules worked, if you had a node like an IMP or any piece of equipment to which two carriers' lines were connected, the carriers involved all had to agree. So if you took a link from the U.S. to Norway, just those two carriers had to agree. When you took it from Norway to London, and that was a British Post Office, now all three carriers had to agree, and that happened pretty easily. When we tried to get, or Larry tried to get a fourth line from London to Stuttgart, the Post Office and the Deutsche Bundespost agreed, the Norwegian Telecommunications agreed, but the U.S. carrier did not agree because they said we could just give you a line directly from the U.S. to Stuttgart. And that was expensive. And the agreement that Larry had worked was actually for a military line from England to Stuttgart. So not only were the CCITT regs a problem, but the way it was structured, they now had military and commercial. And I remember all the interactions with the British Post Office at that time. I mean, even the Queen couldn't get them to do a cross-connect between the military side and the civilian side. It was just not going to happen, period. So it was a showstopper. We finally managed to convince the British Post Office that we really needed this, and they didn't have any capacity on the civilian side. 2 years later or 3 years later, we got a 300 baud line for 10 times the price. And the party in the U.S. that wanted it was the director of DARPA, was Steve Lukasik, and he was gone from DARPA before it actually got put in. So he was having no part of that either, and that led us to go down the packet satellite route, because if we used Intelsat, which was the only satellite system that was really viable then, we had no domestic satellites, that already had built-in agreements between all of the parties to allow sharing of the satellites. And so then we just had to negotiate the tariffs, because they only had point-to-point tariffs and unidirectional broadcast tariffs. So we had to get a tariff that would let anybody sort of deal with it like an Ethernet in the sky, which we did. And there's a paper that I wrote on the politics of this that was in the 1979 NTC conference, I think maybe here at this hotel, or maybe it was the one next door, that laid out the kind of the negotiations about the politics.
So, but I'd like to stay focused on the technology for a second here, because the fact that that you started a mobile packet radio program, and Larry started and you managed to continue the packet satellite program as distinct networks, were, in my view anyway, partly motivated by trying to use this technology to assist the Defense Department in command and control. And in order to put computers at work doing command and control, that meant they had to end up in ships at sea and airplanes, mobile vehicles, as well as fixed installations, which is where the primary computers of the ARPANET were. I mean, they were in fixed locations in air-conditioned rooms, and they certainly didn't get up and wander around. So at the point where you are entering into this multiple network environment, you sort of induce the problem of having to find a way to interconnect these networks, because they were distinct. And even more interesting, I think, is that Xerox Palo Alto Research Center, which is a few miles from my laboratory at Stanford, in May of 1973 invented the Ethernet. And the Ethernet had the property that it was a dumb piece of coaxial cable, which meant that it wasn't smart enough to retransmit packets on errors. In fact, the packets would collide with each other and they would be lost in that common transmission medium. So that was an instance of a very lossy network which had no ability to recover on its own. The computers at the ends of the various Ethernets would have to be the ones that are recovering. Packet radio environment had a similar problem, because the mobile vehicles had changed their connectivity. Packets would be transmitted but not necessarily heard. So we were surrounded by communications technologies that had lossiness as part of their characteristic. So the difference between the original ARPANET protocols that Steve developed with the network working group, and relied fairly heavily on the underlying reliability of the ARPANET, could not be applied to this much less disciplined environment, which led to reinvention of the end-to-end protocols, which we call TCP/IP.
Let me give Steve, credit here for a comment that he once made to me. I had said to him that the real benefit of the TCP protocols that we developed was to deal with that issue, in part, not entirely, because addressing was also a big issue. But he said that the reason they did the NCP protocol the way they did, I'll give him a chance to contradict that if I'm stating it wrong, was because BB&N had told him the network was going to be perfectly reliable, and therefore they didn't need to do that. Otherwise, he might have gone a different way with NCP. Well, you can give it to Steve to comment, or whether you think I stated that correctly or not.
Well, yes. I like all these guys, and we've all known each other for a long time and have very high mutual respect. The BBN crew, Bob and Dave and the ones who aren't here, Frank Hart, Will Crowther, and so forth, as I mentioned, were very focused and very measured in the way that they developed the network. us graduate students from these other sites were much looser and not as well organized. We had our first interaction Valentine's Day 1969, if I recall, in the middle of a pretty terrible snowstorm in Boston. We had some of our tentative ideas that we brought to the meeting, and one of them was that we were going to have checksums at the host-to-host level. And Frank Hart reacted quite vigorously, quite strongly. He said, "You're going to make my network look slow," and he counseled us against checksums. And we didn't have in mind that we were going to retransmit. We thought the network would be reliable, but we wanted to detect configuration errors. Actually, the suggestion from Jeff Rolifson, who had a lot of experience in operating system and file system design, said, if you can detect errors at the different layers in the architecture of the software, then you'd be way ahead of the game. So we had that penciled in our discussion, and Frank pushed back quite hard on that. There was a huge difference in stature. We were youngsters, and he was an adult. It was the short version. And I challenged him a little bit. I said, so I understand you've got strong checksums between the imps and you retransmit, and so I have no issue there. But I said, a wire that's going to connect the imp to a host, and it's a bit serial line, 100 kilobit. How reliable is that? As reliable as your accumulator. Rings in my ears all these years later.
Really?
We later put checksums in a lot of places in the program because memory bits drop out and so on.
One of the, as it turned out, it would have been better. It was already clear to me. I was in the middle of the design of the basic host-to-host protocol that later became known as NCP. TCP was the replacement of that. I would have been happy to see TCP-like protocol earlier, so I had no objection to phasing out NCP and going over to TCP. This is part of the maturation, part of the learning process in the whole thing. Indeed.
So we have a few minutes left, and we can do one of two things. We haven't really touched very much on the evolution from the end of the development stage of ARPANET host protocols to the evolution of Internet. We can't do that in 10 minutes. I do want to at least draw attention to one important theme in the evolution of Internet, and that's the role that the National Science Foundation played. I was reviewing a lot of their involvement, and they got into this around 1980. This is well after the ARPANET had been turned on in 1969. They became interested in, after they saw all the various departments that DARPA was funding, making heavy use of sharing the resources, decided with the 4,000 or so universities that they support that they should get them hooked up as well. And so they began working on a computer science department network around 1980. Then
called CSNet.
CSNet. And then in 1985, they were working on supercomputers. They were funding supercomputers and realized that in order to make them useful, they would have to be networked, and that the universities would have to have a path to get to those supercomputers. So they decided to build a backbone network like the ARPANET, which they called NSFNet. The first one was a 56 kilobit system that instantly congested, not because of a protocol problem, but because of the demand.
Right.
So then they tried again around 1986 or 87 or so with a 1.5 megabit version, which rapidly evolved to a 45 megabit version. They made some other really interesting decisions. Because the Internet architecture allowed multiple networks, they decided instead of having 4,000 universities demand service of one NSFNet backbone and drive the operators of that backbone crazy, they said, why don't we build intermediate level networks? So they had 8 regional networks that would service the universities, and then there were only 8 customers for the NSFNet backbone, which made life easier for them. So they induced a multi-network environment very early on in their planning. And then when commercialization started to happen in the late 1980s, they realized that they didn't need the backbone that they had built, and they shut it down in 1995. Yeah. But they built these network access points, or funded them, so that all of the intermediate level networks that had been connected by the NSFnet could be interconnected at these network access points, so nobody lost connectivity. So I want to emphasize that the sequence of decisions made by a research organization, NSF, in some sense propelled a lot of the commercial development of the Internet by the decisions that they made.
Mm. Yeah, I would add to that, you played an important part in that whole activity as well, as I recall. I got a call from a fellow named John Pasta, who was at NSF, and in the 1970s, I think maybe because of the lingering effects of the Vietnam War discussions that had been going on, particularly in the academic community, the relationship between ARPA and NSF had withered, I would say. There was not much going on between the two. And so I was running IPTO at the time, and I think John may have had a similar position in NSF, if there was a similar position. And he said they were holding a meeting at the University of Wisconsin. Larry Landweber was going to host it, and was to sort of talk about their networking plans for the future. NSF had tried to build a network called FedNet in the early 70s, and it had gotten shut down by the government for a variety of reasons, but it wasn't really clear that it was going to be controllable the way DoD could control a network, that it might expand further. So the Congress did not fund that network, but NSF was trying to figure out what to do for the research community. Because they started out with the assumption that even though the ARPANET was a big success at that point, NSF couldn't get on it because it must surely be restricted only to military parties. Wasn't true, but so we had this meeting, and I went out, and I thought it was an amazing turn of events because it was opening up potential for dialogue. And I could only make a day trip, so I went out in the morning and came back, but they basically started out by assuming they had to build their own, and they were going to do it on a commercial net that had just been available to them called Telenet, that Larry Roberts had actually left ARPA to become the second president of. So while I was there, I challenged them on them. I said, what makes you assume you can't get on the ARPANET? So, because we know it's a military net, we can't get on. I said, look, I'm not prepared to say that's the case. Nobody's ever asked. If you wanted to make a request, I'm pretty sure you could get approval to get on, so think about it. So after I got back home, they came back and they actually made a request to put 4 nodes on, and one was, I think, at the University of Washington, Purdue, Delaware, I forget, somewhere in the Midwest.
Wisconsin, I think, was on too, University of Wisconsin.
Maybe Minnesota, I'm not sure. And so I remember having those discussions with C3I in the Pentagon, and they took the very firm view that, look, if that's what you want, fine, but make sure that the Russians can't get on, or something to that effect. I mean, it was, and so I went back to NSF and made the same kind of comment to them. Anyway, they ended up funding 4 nodes. It all worked out. And the reason I know is I sent them a letter and basically said, you have approval to put these 4 nodes on, and we told them what the pricing was. Back in the mail comes a postcard from NSF saying, congratulations, you've been selected as principal investigator on your proposal. So they treated it as a normal proposal that went in. And so that happened, but they only funded 4 because they thought the cost of doing it was too high. And they instead went with a Telenet connection, which broke into 2 pieces, one of which you handled, which was how are we going to make this happen technically. The other was the politics of it, because they felt like if we were going to connect ARPANET to Telenet, that all the Telenet costs associated with the ARPANET should be paid by DARPA, but none of the NSF costs for using ARPANET should be paid by either NSF or anybody else. And I said, well, that's a bad assumption. I think we should just not worry about it. You pay the Telenet-related costs, we'll do the ARPANET one. Can't do that. And so we ended up saying, okay, then the defense policy, which came back to them, was that we will charge you exactly what you charge us. They said, well, then what's the point of it? And we said, exactly. And so that's how it ended up. That's how it ended up working out, and that worked out fairly well for a while. When they decided to go link the supercomputer centers, that was a whole other kettle of fish that I won't go through all the details. It took some strange turns, which eventually had NSF wanting to work very quickly into a defense regime that was almost required to work slowly because of all the demand on them. They were growing the DDN from 50 nodes to 4,000 nodes, and then NSF wanted to put a few more in with priority. It couldn't work, and they went their own way.
So of such bits and pieces is history made. We've run out of time, but we all thank you. I want to thank the panel very much for all of your comments, and thank you for joining us this afternoon.
Morning, everyone. So we're going to take you back in time, take you back 50 years. We're going to explore what the computing world was like in 1969. That, of course, was the year that the first humans landed on the moon. It was the year that the Boeing 747 was introduced, and it was the year that Woodstock, the rock concert, happened. So let me introduce our panelists. First, Vint Cerf was a graduate student at UCLA. You're going to hear that a bunch. See? He had met Steve Crocker, who's our second panelist, while they were at Van Nuys High School. Steve was both an undergraduate and a graduate student at UCLA. Len Kleinrock was, of course, a professor at UCLA, working on computer networking. Wow. Charlie Kline was also a graduate student at UCLA. And Bill Duvall was a young programmer at SRI up in Menlo Park, working in Doug Engelbart's Augmentation Research Center. He left UC Berkeley after taking all of their computer science courses. So, Charlie, why don't we start with you? How did you end up writing software for this machine?
Well, I had gone to UCLA as an undergrad, and I'd already learned to do some programming from my dad. So I ended up...
Oh, okay, I'll be in the little height.
Go ahead.
So I ended up having to take a programming class, and went to the department chair and said, do I really need to take this? And he said, no, you don't need to. Why don't you work on my research project? So I was working for Jerry Estrin on the research, and then Len got this project to work on the ARPANET. And most of us switched over to Len's project. And I was working on trying to keep our computer system working and working on the operating system. And then when the end came, I had to write some software to make it work.
And you were building an operating system mostly, though, right? For something called the Sigma 7.
Right.
Okay. And how did you end up being on campus at 10:30 tonight 50 years ago?
I enjoyed programming. I sort of describe it as when you got a programming working, it's like moving up the next level in a video game. You got a little excitement. So I would often stay late at night. Sometimes I stayed all night and programmed all night and then went to my classes in the morning. Okay,
so the first connection that you had with Menlo Park was not seen as a big deal.
Not to me.
And why did you pick October 29th, 1969 to do it on?
I'm not sure there was any specific reason for that date. We were ready to try it. Bill was ready to try it, and we started trying it.
Bill, how did you come to be on the other end of that communication?
How did I come to the...
Be on the other end of that communication?
Well, basically I was working with at SRI with Doug Engelbart and his group, and that's where a lot of the paradigm that we see today on the internet came from. The idea of using a computer, which up to that point had been used for basically databases for bank and for numerical processing. The idea of using it as a page-oriented with a mouse information system. And in fact, that's where he invented the mouse as part of that whole effort. But part of the concept was that there would be basically a lot of workstations, or a workstation, he called them knowledge centers, basically. And these would all have these types of terminals, and they'd be connected by a network. And so when the idea of the ARPA, and it was being funded by ARPA, so when the idea of a network came along, it was a very natural step to say, we'll be one of the first nodes.
You and Charlie hadn't physically met.
No, in fact, we never physically met until I think 10 years ago or 15 years ago.
Yeah.
So.
But you did regularly talk on the phone.
We did talk on the phone. When the IMP was delivered, which was, I think, the beginning of October at SRI, along with the IMP came a deadline, and the deadline was October 31st to basically have a login from one computer to another over the ARPANET at that point. And so we worked furiously to try and get all the software ready to do that. And in order to we knew that everything was, there were a lot of things that we were putting together. It was a complicated system, a lot of pieces. And so we decided to start testing early. And that's why it was October 29th, to see if we could beat the deadline. And so we scheduled a test for 29th. It was at 10 o'clock at night, because there were other people that used the system during the day. And we knew that it was fragile, to say the least. This was pre-alpha stuff.
Okay. Now, but also, this wasn't your primary job at the Augmentation Research Center. This was something you were sort of called in at the last moment to do?
That's right. Yeah, there was a person had been contracted to do the interface, and when the IMP was delivered, doing a review of the state of the software, it was obvious that it wasn't going to get there. And at that time, I was the only person in the group that both understood the protocols and could work in the SDS 940 time sharing system. So I sort of, I was volunteered, let's put it that way. And
so this was the Watson come here quick moment of the internet, and nobody really knew that was the case for maybe a decade or two. Is that right?
I'm sorry.
This was the Watson come here quick moment for the internet, except that came much later.
Yes, that did come later, but. It was
actually, and also, even though we talk about messages, it wasn't email communication. The first phrase that you guys were dealing with was login. And what were you logging into?
Well, Charlie was logging into the SDS 940. Basically, so UCLA was logging into the time sharing system at SRI.
And that was called the online system, is that right, or NLS?
NLS ran on the SDS 940 time sharing system. So it was basically a subpart of that system. And the initial login was simply as a user, later to be an NLS user.
So you hadn't even gotten to the application layer yet.
Yeah, exactly.
Well, so then let's talk a little bit about how this came to be. Steve, there was this process called request for comment. And I think that if you could explain that and how that came to be, because that was really where the architecture for the system came from.
The basic plan for the ARPANET had been laid out by the adults. We were the kids. So the IMP was designed by Bolt, Brannick, and Newman, and the long lines, the telephone lines that were procured from AT&T. And then what seemed, in a way, an afterthought was, okay, we've got to get some software running on the hosts to talk to each other. There was a meeting called at Santa Barbara, UCSB. Elmer Shapiro from the SRI group chaired the meeting. Vint and I drove up. Did you make the choice to send us up there? Somebody said...
I wanted to go the cheapest way. You kept busting my budget.
That came later. The trip to Santa Barbara was cheap. The expenses grew after that. So Vint and I grew up. This was August '68, so this was more than a year before the time that we're talking about. The contract for the IMPs had not yet been let, but it was in process. We met counterparts from the other groups. Bill, were you at that meeting? Jeff Rulifson was there, I remember.
Yeah, I was there. Yeah, it was Jeff Rulifson, Eric Harslam, Elmer Shapiro.
And And it was a pretty interesting meeting in that there was not much of an agenda. We all came with to find out what was going on, and it was sort of like a cocktail party engagement where you instantly click with certain people that you can tell you're on the same wavelength. And we could see that this communication was going to be more interesting than just logging into a remote machine or sending a file. Those were obvious. We obviously wanted to be able to do that. But we could see a bigger picture. And we kind of self-organized after that and decided that we would keep talking. And in the process of keep talking, we said, well, we should visit each other's laboratories, which is where Len's comment about busting his travel budget came from. And we understood the irony right at the very instant that we said that this network was supposed to make it possible to collaborate at a distance without having to travel. And the first thing we did was lay out a whole travel schedule so we could visit each other's laboratories. Those meetings were we engaged in large and small topics. The specification for the fine-grained communication had not yet been specified because BBN was not yet working on this and they hadn't published their interface specification. So we looked at sort of the bigger picture. What kinds of things would you want to do? We sketched out a number of interesting ideas. And we did this just sitting around a table in these occasional meetings every 6 weeks or 8 weeks. And then in the spring of 1969, so about 6 months before the date we're talking about here, we said, well, we should start writing down some of these ideas. After all, we're supposed to be academics and we're supposed to be, doing research, so we should write something down. So we dealt out assignments to each of ours. You write this, I'll write this. And then I casually offered that I would organize the notes, which I didn't think about it at the moment, but over the next couple of weeks, every time I sat down to write what should have been a trivial administrative clerical note, I found myself balking big time. I had trepidation, and I realized what it was that the act of writing these down might make it look like these were official, important, authorized, and I was very fearful that some adult was going to come from the East. I didn't know whether it'd be from Boston or from Washington, but who are you guys, and who gave you authority to do any of this?
Let me quote from RFC 1. You wrote, "Very little of what is here is firm, and reactions are expected."
That's right. That's right. Yeah. So late one evening when I was determined I had to write something down, I said, look, these things have no status, no authority. Write as little as you have in mind. You can write questions without answers and so forth. Bill had suggested the term request for comments. I hadn't remembered that until recently, but it stuck in my mind. And I said, just as a matter of form, we will make every one of these notes called a request for comments. I figured it was a temporary hack, last maybe 6 months, until there was formal documentation of this network. We numbered, the other rule that I put down was that you had to write it before I give you a number, because I didn't want a lot of holes in the sequence. And so that seemed to work pretty well, except that it didn't stop. It just kept going and going and going, and when I was asked, we did an index of the first 100, and then when I was asked to write something for the first 1,000, I thought this is a sorcerer's apprentice kind of situation where you can't turn it off.
So there are about 8,800 RFCs
today.
Well, and they're not the same, because in the early days we had no other way of communicating. We sent these out by snail mail, by U.S. postage. We had a mailing list, and in fact, the mailing list was maintained as one of these RFCs, and every time we added somebody to the mailing list, it was another RFC.
Bill remembered that you guys flipped the coin to see who would write 1 and 2. Is that your memory?
I lost. I got RFC 1.
I remember it the other way. You won and got RFC.
What was remarkable to me about RFC 1 is it was about 2 experiments. Did you guys know much about the online system when you actually set that up?
We had visited, this process from August 68 to spring of 69, we had now visited each of the laboratories. What was remarkable, particularly in retrospect, was the SRI laboratory, Engelbart's lab, They had invented the mouse, and ordinary people didn't see it for another 30 years or something like that, approximately. And a graphics interface with hyperlinks and structured text and everything. So the future was sitting right there, and better yet, it wasn't just you could take a tour and see it in the laboratory. That group was using it every day. That was part of their basic thing, and so it just had to wait till it became commercially viable. But we were living, at least thinking, in a mode of this is the way the world is going to be, and we're going to lace it together with this ARPANET. And how could we make it flexible enough so that it can accommodate the future technologies that were coming along?
I want to ask a little bit about the culture of those laboratories at the time that you guys were doing this work. You guys both started early, Steve and Vint. You started as high school students, spending regular time on the UCLA campus, is that right?
Oh, yes.
Breaking in even on occasion.
I was afraid you were going there.
No, wait a minute. Steve got permission. No, wait a minute. Steve got permission from Mike Malkinoff, who was chairman of the department at the time, to use the Bendix G15 paper tape-based machine at UCLA, and I think eventually we got to use the 7090. So we had permission, but one evening we showed up, or maybe it was a weekend, we showed up, and the door was locked. And so what happened then, Steve?
So, statute of limitations is passed. Vint and I had been playing with some silly equations and decided we would try to explore them numerically. At least sounds better now than whatever I was able to say. So this Bendix G15 was in a building that called Engineering 1, which I believe is now gone. But I did have permission to use it, and we arranged to come over from Van Nuys High School in San Fernando Valley. It took a little less time to do than it would take today, I think.
The dean is in the audience.
Tell everybody. So we came over on a Saturday, and the building was locked, and I was crestfallen. Two of us are standing there staring at the door, and Vint notices that the second floor window is open. It's one of these crank things. And I'm thinking, we're not really going to. Next thing I know, he's on my shoulders.
I always have, that was the beginning.
He goes through the window, he comes around to the main door, pushes the bar open. We taped the door so that we could get in and out easily during the day to go buy some food at lunchtime or whatever. Nobody else was around. The interior doors were all open in the office. This is long before student demonstrations and all other kinds of things that have beset us. And we worked all day, and we cleaned up afterwards, and we went home. That was spring of '61. 11 years later, in '72, I'm working for the Defense Department. I've got a top secret clearance, and the Watergate burglars break in, and they tape the door. And the guard, who's one of their cohorts, who's in the hotel across the street, is on lookout, but he doesn't recognize the threat because the security guard who found it was in plain clothes. And the shiver that went down my spine was something.
So, go ahead. You can tell your story.
I was at the White House in 1999. Hillary Clinton was doing her Millennium Evenings, Honor the Past and Imagine the Future. And she told that story.
Yeah.
So the question is, how the hell did she find out about that?
I didn't.
It was on the internet.
Oh.
So, Stephen Levy has written a book called Hackers. That the term hacker meant one thing before it meant something else. And when you guys were first computing in the 60s, a hacker was someone who was really sort of obsessed with computing. And there was a laboratory at MIT, the AI lab, where this culture grew up. Would you call the culture you guys were created both at Menlo Park and LA similar? Was it a hacker culture in that first sense of shared information?
Well, it was MIT that adopted that term. You were there.
I was there, but there was an interesting story. These guys, again, are guilty. There was some guy on campus that committed some terrible break-in to a computer system. they decided to hire him as a programmer. I mean, smart guy. You fired him a few months later, right? Didn't work out.
It was a question as to whether he could learn to do something other than breaking into systems, particularly if we said, look, it's not interesting. We'll give you the keys to everything and see if you can do something constructive. And
so a hack was a really cool piece of software, and a hacker was somebody who produced really clever code. And that was an honorable title for many years.
Yeah. Bill, was the culture the same in Menlo Park?
No, I wouldn't say it was at all. It was, the culture in Doug Engelbart's group, the one that I was in, was basically almost self-contained, and people were very focused on this one vision that we were working on. And although there was some connection to the outside and interchange, it was very little. The group was in and of itself was a little bit odd, and for SRI it was generally disliked, I guess I would say. It was certainly not understood. I mean, they did things like, we'd work at all hours, and we'd have Friday afternoons would be for wine and beer, and this was very un-SRI-ish. And one of the things I remember is when I was interviewing to join the group, the last interview had to be with the head of the engineering department, and he sort of asked a few questions. Why do you want to do this? And I was saying, this, what they're doing that's the future. That's what I want to be with that. And after a while, he sort of thought about it, and he looked over his desk at me, and he said, "Son, you don't think what they're doing up there is science, do you?"
John, you're talking about the culture of the period, and there is a very strong component that mattered and helped create what we have today, and it's the way in which the funding took place. I think you're familiar with the story, the way ARPA funded the various centers, the universities, and just, they would go to a great researcher there and say, here's a pile of money. Go do something great. Shoot for the moon. Failure's okay. Go high. Keep going. You have the money for a long time, and we're not going to watch you. Now, what else could you ask for? It was an environment that just generated creativity. It was a golden era. And when that came to a principal investigator, passed it off to these guys, same idea. They complained we didn't supervise them. I said, go do it. Yeah. Eventually, if you want something, come back to us. And they ran with it. You just hear the stories, the way they organized themselves and created this community across many universities was a very important component that gave a lift to this whole project.
Well, and how quickly did that end? And was it the Proxmire amendment that ended that era?
Not totally, but it hurt a lot. They said basically it has to have a military application, has to be competitive. You go to a guy, here's the money, that's not competitive. It's not peer-to-peer, but it worked.
Okay.
Well, on the other hand, ARPA has some pretty smart people. And so they created this thing called a broad area announcement, which said this is the area in which we would like to explore. Would you like to submit proposals for that? I think we managed to induce the right people to submit the right proposals, and the longevity of support from both NSF and DARPA is countable in decades. And so that's still true today.
It's true. But your point about having really good people at the government deciding where the money should go, people like these two here, they were at ARPA, that level of capability, looking out and finding the projects to support. That whole thing worked so well.
I want to ask about the design of the network, but before I go there, a lot has been made of the first crash, and I want to ask a different question about the first crash. When you type G, there was what is known today as a buffer overflow error, and the machine crashed, and you had to fix that problem, and you started over again. What struck me when I learned about it for the first time is that buffer overflow errors have continued to plague the design of computer systems ever since. And in fact, you might say they're one of the real vulnerabilities in the design of modern computing. What I don't understand is, when Robert Tappan Morris, for example, brought the internet to its knees in 1988, the then young internet, he used a buffer overflow error. Why didn't the designers?
Because
I can answer that.
Okay.
It's because they didn't talk to me.
right.
Well, walk us through that.
No, it's stupid mistakes.
There are sort of two answers to this. One of them is that the initial specification for the first connection was that all messages would be 1 character in length. And because of the way that the 940 time-sharing system worked, when you typed a character on your terminal, it didn't appear on your terminal. It went to the computer, and the computer then sent back that character. That's called full duplex. And the 940 had what they call command recognition. So as you were logging in, as soon as it realized what you wanted to say, it would send back the rest of the command. So when you typed an L, you got an L, an O, you got an O, and a G, you got GIN. Well, that's 3 characters. And there was no memory available. And memory was very, very tight in the 940. And so when I was allocating buffers and things like that for output, I allocated 1 character because that's what the spec said. And 3 came along and there was a buffer overflow. Now, that seems to absolve me, but the problem is I wrote the spec.
So what you don't know about Bill is he also wrote both the first assembler and the first compiler for the Macintosh, and has gotten very little credit for that, but you're probably using some of his code somewhere.
Yeah, thank you.
So, Len, tell us the story of how you came to put together the networking group that actually sort of did this on your end.
Well, I came to UCLA having this theory in my hands, waiting for it to have it implemented. Finally, as I said, ARPA said, let's build a network. So I had to get this group together. As Charlie said, he was working with Jerry Estrin. Jerry Estrin had put together a group of great programmers doing a variety of things. When we got the contract, the whole group moved over to me to jump on this really exciting project. So that's how this group entered the picture. And they continued to run with it beautifully.
So what about the design ideas? Packet switching seems to be kind of a non-obvious idea. And what was the networking theoretical world like when you were starting this process? And why did you, what attracted you to packet switching?
So there was no world. At the time, nobody was thinking about data networking in a serious way. And all my classmates at MIT were working on information theory and coding theory, which Claude Shannon had solved fundamentally. And the problems that were left over were small and hard. And I was dragged in to do a PhD. I didn't want to. My supervisor said, you got to do it. So I said, if I'm going to do it, I want to do something with impact, and I want to get the best professor I know. So I spoke to Claude Shannon. You may not know his name, but he's a great man. He took me on, and I looked around, and I was surrounded by computers. And I said, one day they're going to have to talk to each other. And the telephone network was woefully inadequate. So I looked at this problem. Here's a new problem. If it can be solved, it will have impact. And I had an approach. I knew how to basically extract the essence of the system, which had to do with what we now call the sharing economy. It's called Airbnb. If you've got a room that's not being used, if you've got a communication channel that's not being used, let somebody else use it who needs it right now. That whole idea of dynamic resource sharing was a principle that I put into the theory. And the whole idea of the packet switching, I analyzed a case where you would chop messages into fixed-length things called packets and handle them one at a time. And that had some advantages. So that whole thing came together. I had done the analysis, did an optimization, and then stood around and extracted the principles as to why this thing works well. You know, most of the students these days don't bother to do that. You know, they get a result and okay, I'm done, instead of saying, what is it teaching me? And we extracted some principles like dynamic resource sharing was key, like big systems are better, wanted to study a large network, millions of nodes instead of tens of nodes, because then you get emergent properties you don't see in a small network. And looking at distributed algorithms, distributed control, and recognizing nobody's in control when you have a large network, but you can't get one node to be in control because there's too much traffic, too vulnerable, too much traffic going in and out. So distribute it. Once you distribute the control, nobody's in control. So will that work? So you had to prove it wouldn't collapse. You could chop pieces, it would still work. So those are the kinds of things we extracted. Came to UCLA with that, waiting to build it. The opportunity came along, as I said, and bang.
And it was a DARPA-funded opportunity? Is that what you're talking about?
ARPA-funded.
ARPA-funded opportunity, right.
Yes.
So let me jump up a level, and there's, for many years, been a debate over whether ARPA was funded or in some way backed because of the design was about survivability in the event of a nuclear war. This is hotly controversial. Is it wrong?
Yes,
So
it is.
It's an urban myth, but there's some truth to it.
Okay. Lukasik apparently made that assertion.
Look, in the video that you saw, you could tell that Taylor and Roberts were trying to figure out how to share computing resources among about a dozen universities that were studying artificial intelligence and computer science for ARPA in the 1960s. They couldn't buy a new computer for every university every year. So they said, we're going to build a network and you're going to have to share. So the whole idea, and papers that Roberts and Barry Wester wrote were about resource sharing. Even though some of the early ideas of packet switching came from Paul Barron in a study that he did at RAND Corporation, and that was about building survivable networks for post-nuclear responses or post-nuclear scenarios. So we should not conflate those two things. Okay. The subsequent internet design, however, did go after this question of survivability in a post-nuclear environment, and we even tested that idea because we used the packet radio system and put radios in the Strategic Air Command aircraft, artificially broke up the ARPANET into pieces, and then glued it back together using the TCP/IP protocols and packet radio. So there is truth to some of this, but it wasn't specific to ARPANET as much as it was to the subsequent.
You know, once Steve,
yeah, let me. So this is, as to say, is a sort of a persistent myth, and the question is to what extent there's truth there. And it's subtle because there's various layers. As Vince said, Bob Taylor and Larry Roberts are all focused on how do you build a system that would allow the computers to communicate, people to communicate, share resources, and the degree of survivability, quote unquote, had to do with just normal operation. I mean, parts are going to break, lines are going to go down, and so forth. When you talk about survivability in a much more stringent sense, you're in a different part of the design space. And it isn't just all or nothing, because the worst case, the one that attracts everybody's attention, is imagine nuclear holocaust, and nobody's ever really focused hard on that problem. And I'll come back to that in just a second, because I spent some time with Lukasik over the past couple of years having a discussion about that. But you also have, apropos of what Vint talked about, that you have stressful situations, particularly in the military, that are more stressful than ordinary daily operation, but less stressful than the Holocaust kind of, total catastrophe. And the kind of survivability and knitting the pieces back together again are important experiments there, but they still won't take you all the way to what do you do if, in the worst case. The other part of the story that I think is very important is this culture of initiative that you described played out in multiple layers. So you have the agency, ARPA, which later became known as DARPA, which was created after Sputnik. And inside, you had a division into various offices, and the office that was of concern to us was this Information Processing Techniques office. And there was quite a bit of delegation down to the offices and to the program managers, and more importantly, even to the researchers themselves, the principal investigators, to invent the projects. And so there was as much bottoms-up kind of operation and choice of topics and so forth as there was top-down. It was not a dictatorial thing like we're going to build. This is sort of different from saying we're going to put a man on the moon and everything gets organized to that one objective. It was much, much broader. So the problem that the director of the agency, there were a series of them, but Steve Lukasik was central for a period of time, has is how does he provide the support for all of these projects to go forward and justify that to the higher levels of authority in the Defense Department and Congress. So a conversation approximately like this took place. Lukasik says to Larry Roberts, well, could it solve the reconstitution problem? And allegedly the answer was, well, I suppose. And There's no paperwork on this, except that years later, Lukasik wrote why I signed the checks for the ARPANET, and included in there is a little reference to nuclear survivability. But Roberts, I pressed him on that a couple of years ago. I interviewed him, and he said, well, if I'd really been trying to solve that problem, we would have connected every imp to 4 other imps and so forth. So, and clearly down at the levels that we were working at, there was absolutely zero attention to that. We were working on the problem that affects us all today. How do you get people to talk to each other? How do you get the computers to talk to each other? How do you accommodate the differences among all these systems and get them so forth? And we were not at all focused on sort of the hardcore defense problem of the day.
Wait a minute. I'm sorry. I really feel compelled to jump in here because there are 2 different things that we're talking about. We've been talking about the ARPANET. That's what this big celebration is about on the first connection of the 2 hosts. But I really must insist, Steve, that when Bob Kahn and I started to work on the Internet design, it was driven by the idea that we would use these technologies for command and control. It was very driven by exactly a military requirement. And that's why we ended up with satellites and mobile radio, as well as the original ARPANET. So I want to make sure that it is not misunderstood that the motivations behind the original TCP/IP work was somehow only to do with civilian applications, because frankly it wasn't.
Yeah, no, so this is the area where it takes some care in describing, because of course, and the projects and the orientation that you're working on is very important. What I was trying to say is that that kind of application, the command and control and reconstitution in the case that you lose various pieces, is qualitatively different from trying to imagine a post-nuclear exchange environment in which
I accept that, although I will argue that we tried to test at least some ideas that would be needed in order to contribute to that solution, and that's why we did the artificial breakup of the ARPANET.
Yeah.
So you mentioned packet radio and wireless technology. In the early 70s, ARPA began to fund research in that direction. And clearly, one of the major applications was military. Soldiers in the field, tanks running around. So there was a shift in what was coming down as to where they saw the applications was the basic networking, the internet stuff that we were doing, the ARPANET, had no expectation of military application at all.
I'm also very interested in how this distributed architecture won the day. When I showed up as a young reporter in the early 1980s, IBM was pushing this idea of a token ring, and there were many centralized ideas around. Actually, before I get to that, all the computing you guys have talked about, IBM and AT&T generally don't show up in that community that you were building. They were kind of the dominant. Why was that?
Proprietary network. They were pushing it. If you had an SNA network, an IBM SNA network, right, you bought IBM equipment and you used their communication protocols.
But wasn't IBM and some of those large companies, weren't they also skeptical about the idea of this project? I mean, they didn't even bid on it, is that right?
They were not skeptical about networking because IBM had SNA, Digital had DECnet, HP had DS. They wanted to network their computers, but they wanted only their brands of computers to be interconnected, and the Defense Department didn't want to end up trapped in one particular brand of computer for purposes of networking, which is why the heterogeneous interconnection of different brands of computers, which was demonstrated on the ARPANET and then subsequently expanded to allow multiple packet switch networks to be interconnected, was important to the Defense Department.
There's multiple times here. If you look at 1972, for example, when the public unveiling of the ARPANET, a few people from AT&T came and looked at it and turned up their nose and walked away. You talk about later in the late 1970s, and then IBM and AT&T, others are all pushing networking of their particular flavor, and then it took a while for it to settle
And if you go back to '68, when the IMP project was being, the RFP for the IMP was, AT&T and IBM both refused to bid. They both said, this is a waste of time, it won't work.
Yeah.
AT&T finally launched in 1983 their great network called Net 1000. 3 years later, they closed it down with $1 billion loss because they couldn't do it. The technology is not trivial, and they, stiff-armed it, never got it going.
Yeah. Let me throw in a couple of questions from the audience. At what point did you start to think about the social and other impacts of your research work, e.g. equity, inclusion, and business?
Well, I think the first demonstrations of email, which came in mid to late 1971 with Ray Tomlinson, demonstrated that very quickly after that.
So email was not on the ARPANET in the first 2 years.
No,
That's right.
Yeah.
No, it was a development that it was foreshadowed by the use of time-sharing systems for email among the participants on the time-sharing system. Tomlinson at Bull, Baranek, and Newman figured out he could use file transfers to move messages from one machine to another. It only had to say which machine was it going to and for whom. So we used the only character on the keyboard that wasn't already used with other operating systems, the @ sign. That's why you have user @ host as the basic form for email. So as soon as email popped up and we all got excited about it, we started seeing mailing lists, and that's when I realized that there was a real social element to this. The first mailing list I remember was called Sci-Fi Lovers, because we used to argue over who were the best, science fiction writers. And the next one I remember from Stanford was called Yum Yum, and it was a restaurant review for the Palo Alto area. It's very clear that this technology had a social component.
Do you remember Human Nets?
Yes, I do.
Because that was what drew me to the early ARPANET, because there you had technologists talking about the impact of technology, which was a really interesting window into that world.
There's another story. I'd visit my graduate students, mostly the theoretical guys, not the software developers. And I walked into their lab one day. Instead of doing research as I wanted them to, they were busy on the machines intensely on news groups.
Yeah.
Restaurants, hiking, astronomy. What are you doing? And, oh my God, this is hot. And it really caught on.
With social media. Bill.
Just on that, one of the things that just speaking of email, another kind of social impact was there was a project that was being done jointly between Xerox and Park and a part of Xerox in El Segundo, and it was being coordinated by email. This was pretty early. This was in the 70s, mid-70s. And the thing that became very obvious was that using email to coordinate a project shifted the power. The people that now had the power were not the people that presented well, that could talk well, that were big, but they were the people that could write well. And it was just an interesting, but subtle, but very interesting shift that was a direct result of, basically this distributed, the networking.
Yeah. Actually, just a funny aside, when Bill Gates came to visit the masthead of the New York Times in probably 1992, they said, "How do you run your company?" And he said, "Oh, I use email." And they ordered up what became a front page story about the impact of electronic mail. So we were a little late to that. Here's another question. How and why did the network name change from ARPANET to Internet? And if they could change the name Internet, now what would you call it? That's the perfect name, it seems to me.
Well, originally, we called it, the paper that Bob Kahn and I wrote said, a protocol for packet network intercommunication. Mm-hmm. And it took too long to say that, and so within a year or so, we used the term Internet to refer to the multiple network thing. I don't know what I call it now. Probably a, no, I can't. There's some bad words that occur to me.
Here's another question from the audience. When did you realize that you are an essential part of the historical breakthrough? What did you feel at that time? How long did it take you guys to understand that this technology was going to have the impact that it has had on the world?
1988 for me.
There's another.
What was it about 1988 that made?
I walked into the Interop show, which Dan Lynch started. It was an exhibition. 50,000 people showed up to see Internet technology, hardware, software, and everything else. And I was walking in with Eric Benamou, who was the then 3Com CEO. And the first thing we saw was a 2-story Cisco Systems, display. And I asked Eric, how much does these cost? And he said $250,000. That was in 1988. And my jaw dropped, and I said, my God, people think they're actually going to make money out of the Internet. and at that point, I started thinking, how could the general public get access to it? Because up until that time, there was an appropriate use policy that said no commercial traffic on any of the government-sponsored backbones. So for me, anyway, that particular moment is what triggered my interest in trying to get internet into the hands of the general public by making it commercially viable so it would be self-supporting.
One last word. Steve, was there a moment where you understood it was going to have the impact on the world that it did?
It was pretty evident almost instantly to me that if you had a computer, you would want it connected to the other computers, and that now, in those days, computers were big. I mean, that was a tiny computer by comparison. So universities and businesses and governments had computers. Personal computers didn't exist yet. But it was evident to me that basically would want to have that every computer, if you owned it, you would want it to be connected to the network. And so it was just a question of how long it would take for that to happen. And I thought that was real important from a utility point of view, from a practicality point of view. My head was focused on different kinds of research, much more abstract kinds of things. And so I used to sneer that this networking stuff was only socially useful. It didn't have any real depth.
We're out of time. Join me in thanking our panel for changing the world.
Thank you.
Thanks, Greg.
Welcome, all of you. Before starting with the Pioneers panel, I would like to invite Oscar Robles, LACNIC CEO, to welcome you to this extraordinary event. Please go ahead, Oscar.
Thanks, Maria. So we're ready to begin our webinar. Let me start by thanking first our guests, Charlie Kline, Leonard Kleinrock, and Steve Crocker. Thank you so much for being with us. It is an honor having you here to celebrate 50 years of the Internet with the community of Latin America and Caribbean. And thank you, all of you connected to this webinar. Welcome to this amazing opportunity to chat with some of the Internet pioneers. Last week, we celebrated with the local event in Montevideo with the regional pioneers. In that event, we mentioned two different achievements in the 50 years ago, the moon landing and the first data packet sent over a telecommunication line. The former, the moon landing, received a lot of media attention in comparison with the latter. It was actually covered live during several weeks. But from our view, and I think many of you will agree on this, it is the second achievement, that first data packet sent over the internet or over telecommunications lines, which has been most relevant for human lives. It is that event, that particular event, that has touched billions of human lives. So I will stop here to listen to our guests, and I will let Carlos Martinez, LACNIC CEO, to lead this conversation, and I hope everybody will enjoy this webinar. Over to you, Carlos.
Thank you, Oscar. I will share my video so you can. I think it's a bit friendlier to have a face in the video. Thank you, Oscar. Thank you, Maria. Hello and welcome to all who have connected to this 50th anniversary webinar. My name is Carlos. I will be your host this afternoon. This webinar is organized by LACNIC. LACNIC is one of the 5 regional internet registries, and we are the bodies who are in charge of ensuring that IP numbers are globally unique. And this function, the need for IP numbers to be globally unique, is one of the things that became very important very early on, during the startup of the internet, and we can trace our history to those times. We believe this anniversary is really worth marking, and we have tried to bring to our region the voices of the internet pioneers. If you're here with us today, you're using the internet. I'm not going to describe how the internet has deeply changed society, the huge impact it has had on almost every aspect imaginable of our life. Suffice to say that this webinar brings together speakers and hosts from Uruguay, Canada, where the ICANN meeting is being held right now, and the United States. registered participants hail from at least a dozen different countries. Well, have you wondered how it all began? As Oscar mentioned, it began exactly 50 years ago with a humble packet, 2 tiny bits of information that were transmitted between 2 computers in California, which were both about 400 miles away. Indeed, as Oscar mentioned, the 60s were interesting times, not necessarily for all the best reasons, the Vietnam War, but we had also the space race, the music scene of the 60s. And among these ground-shaking events in 1969, there was the birth of the internet. This event that we will celebrate today has probably had the largest impact on our lives of them all. Today, we would like you to take you back to the beginning of it all, back to those times, and listen directly from those who were there, the stories of the birth of the internet. First, please let me remind you of a couple of things. Please remember to use the chat windows, either in Spanish or English, to send your questions. Please identify yourself, and please identify the person you are directing your question to. And also please bear in mind that those who are listening to the Spanish audio channel, that this channel may have some delay due to the interpretation work we are doing today. So let me introduce our speakers today. We have Leonard Kleinrock with us. Leonard is an American engineer, computer scientist, who has made, I would say, key contributions to computer networking and computer science, and in particular to the theoretical side of computer networking. He obviously, and as everybody knows these days, he played an important and pivotal role in the development of the ARPANET. Charlie Kline, also a computer scientist from UCLA. He studied under Leonard, so this is a kind of I would say university reunion. Charlie played a role in installing the first IMP, which is the precursor to the modern day router, which enabled the packet switching function on the ARPANET. Charlie sent the first successful message on the ARPANET that was intended to be the word login, or at least part of it, and I'm sure we will listen to that story today. Steve Crocker. Steve is one of the, I would say, better known members of the internet community. He has been with us since the inception of what we call the internet community, that ICANN and we, the ARRs, are part of. Steve was the leader of the network working group that led to the development of the ARPANET host-to-host and application protocols. He has been a member of the ICANN board for a number of years, and been also a chair of the ICANN board for several years. Another one of the original pioneers, Vint Cerf, sadly could not be here with us today, but he sent us a few words on video, and we will start our panel today with Vint's video, and then we will give the floor to Leonard first. Can we start the video now?
Hello, my name is Vint Cerf. I'm Google's chief internet evangelist, and sometimes known as one of the fathers of the internet. I really appreciate Maria Gallo's invitation to participate in your celebration of the 50th anniversary of the first linkage of 2 computers across the predecessor to the internet, the ARPANET. 2 nodes at UCLA and SRI International were interconnected by the nascent 2-node ARPANET on the 29th of October, 1969, literally 50 years ago. And that began an evolution which is ultimately concluded in the invention of and the further spread of the internet technology that you and many others use today. In fact, I'd like to thank LACNIC for its role in helping to make the internet useful in the areas of the world where it has responsibility for IP address allocations, to say nothing of helping people make use of the internet in various and sundry ways. So it's fitting that we should celebrate this 50th anniversary of a particular igniting event, but it's also very important to recognize that the internet still has a long way to go in terms of our understanding of how to make it work better, how to make it beneficial, how to deal with some of the negative effects of internet and the platform that is occasionally abused by people who don't mean us well. All of these things will require both technical, regulatory conclusions, or at least regulatory responses, and those responses will need to take place across national boundaries. The Secretary General of the United Nations commissioned a high-level panel on digital cooperation, a report on which was presented to the Secretary General in June of 2019. It called for increased cooperation among national entities and others in the private sector, in the academic community, and the civil sector in order to find ways to make the internet a safer, more secure, and more beneficial place to be in. And I submit that that's part of your job as well. So I hope that you'll take that burden in hand and help all of us make the internet a better place to be. So happy 50th anniversary to ARPANET and the subsequent internet.
Thank you, Vint.
My name is Vint.
So we will start our panel this afternoon. We will start with Leonard. We have a couple of questions, but this is basically, I would say, an excuse for you guys to tell us what you feel the best stories of the birth of the internet are. So the first question is, can you tell us a little bit about the prehistory of the internet? Let's say what was going on between 1957 and 1969, the events leading to the transmission of the first packets on the ARPANET. How did you guys get involved? Leonard, the floor is yours.
Here, on October 4th, 1957, the Russians launched Sputnik, the first Earth-orbiting satellite, and President Eisenhower in the United States recognized that the Russians had gained superiority over the United States in certain areas of technology and science. And so in response to that, on February 7th, 1958, 4 months later, he created the Advanced Research Projects Agency, ARPA, to basically fund science, technology, engineering, math in the United States to bring our capability back up. And they funded schools, universities, research centers in all areas of technology and science. That was one thread that led to a piece of the ARPANET we're going to discuss. And basically what they did is they funded these centers in a variety of ways. And by 1966, they had been funding computer science for a number of years. And there were many centers, research centers across the United States that had built up excellence in specific areas. University of Utah had great graphics. University of Illinois had great high performance computing, etc. And they recognized that it would be a great idea to connect these research centers together through a network which would allow one user at one site to log on through this network to a remote site and gain access to the capabilities at the remote site. So suddenly a need for a network which would connect computers together became real. Now let's go back to an earlier period because there was a separate thread occurring at the same time. As a PhD student at MIT in 1960, 61, and 62, I had decided that I was surrounded by computers and sooner or later, they'll have to be connected together. And there was no adequate technology to allow that to happen. The telephone network was woefully inadequate. And so I decided to look at this problem for my research. It was a new problem. It was important. If I could solve it, it would have impact. And I had an approach to putting together a mathematical theory for how computer networks could be designed, optimized, and how they would perform. So in 1962, I published my dissertation. Meanwhile, independently at the RAND Corporation, Paul Barron had been working on a similar problem. We were completely unaware of each other. He was working on a network to allow the United States to survive a nuclear attack. So this work was going on, and it was available when ARPA in 1966 decided they needed to create a network. So they came to me and they formed a committee of researchers headed by one of my former classmates at MIT, Larry Roberts. He was now employed at ARPA to make this network occur. And so a group of us got together. We wrote a specification as to how it would perform and be designed. This specification went out to industry to bid on winning a contract to implement this plan. The contract was won by a company called Bolt, Beranek, and Newman. They were awarded the contract in December of 1968, and it was decided that UCLA, where I was now a professor, would become the first node in this network to be designed and implemented, because basically we had the technical expertise to understand how it should perform, and were able to then generate experiments to test it and find out where the faults were and how to improve it. The schedule was to bring UCLA online over the Labor Day weekend of 1969, less than 8 months after the contract was awarded to both Beranek and Newman. And BBN delivered the first switch to UCLA on the Labor Day weekend, on time, on budget, up and running. They had created a new technology with new users and new applications in basically 8 months, something that would be very hard to do today. The machine came in, and a month later, a second switch was deployed at Stanford Research Institute, 350 miles to the north, as you heard earlier. And the idea now was to connect these two computers together to test the use as it was designed, namely, sit at one computer, in this case UCLA, log on to a remote computer, in this case Stanford Research Institute, and attempt to log in so that, in fact, we could test the functioning. So that's the background that led us to the day you just described a few minutes ago, Carlos.
Thank you, Leonard. I would like to move to Charlie. Charlie, what can you share with us?
I was working on the operating system for our computer at UCLA, and Len got the project from ARPA to connect us to the internet, and so I had to work on the issues of how we were going to connect our computer to the switch. One of the other graduate students at UCLA was a hardware engineer, and he was able to build the hardware we needed to interface the computer at UCLA to the switch. Each site was responsible for building its own hardware. You couldn't just go off the shelf, and buy something. There wasn't USB standards or any other standards. The actual spec said, here are the signals, here's the voltages, here's the timing. You build something to make it work. And one of our guys did that, and he did an excellent job. And then I was working on the software to try to figure out how to connect to the switch and actually send something to it. And within a few days, we were actually able to send transmissions between our computer and the teletype on the IMP. The IMP actually had virtual computers in it, that virtual hosts they refer to, and one of them was the teletype. So if you sent a message to that address, it would print out things on the teletype. A month later, Stanford got theirs, SRI got their switch, and Bill Duvall at SRI had to do the same thing, and he got his stuff working. And then we tried to see if I could communicate, as Len was describing, to the computer at SRI. Now, his system was somewhat more mature, and he was more able to build the part where if I sent him characters, he could actually interface it to the operating system. So I built an application where I could read characters from a terminal and send them to SRI, and he would take them, send them into the operating system as if they had come from a local terminal. And then anything that was coming back from his system that would normally have printed on a terminal, he would intercept and send back to us at UCLA, and I would print it on our terminal. And it's been widely reported I'm sitting there on a phone talking to Bill Duvall, and I'm saying, I'm about to try this. Let me send you something. Now, his system required you to actually type the word login to log in. So I typed an L, and he on the phone said, yeah, I got the L, and I saw the L printed on my terminal. And I typed the O, and he said he got the O, and I saw that it printed on my terminal. I typed the G, and he got the G, but then he said something went wrong, and it turned out that his system knew what commands were available at that time, and it actually tried to send back GIN. And at that particular point in the code, he had a little error where he didn't expect the 3 characters. So he said, let's try again in a little while. And about a half hour later, we tried again, and this time it all worked. And I was able to remotely log in and do things. And it was kind of neat. I mean, it was late at night, and it was kind of fun. And so that was sort of the beginning. Meanwhile, Steve Crocker, who I'm sure will describe for you, was working on with groups of people about how do we make these systems actually do something other than just log in? How do we make them more general? And to follow on one of the things Len said, there had been some previous networks, but they were special purpose networks. For example, the SAGE network, the Strategic Air Command network, in the late 50s or early 60s, where messages were sent from one Strategic Air Command site, nuclear missile site to another, but they were very special purpose. This was an intent to build a general purpose network, a heterogeneous network where the computers could be any kind of computer and the applications could be any kind of application, not just the limited sets of commands that the nuclear weapons needed. And so that's was my initial involvement. I continued on as the protocols grew to work on the protocols and to implement things. But and my personal computer science research was in computer and network security later on. So.
Thank you, Charlie. Now over to you, Steve.
Well, thank you. It's a pleasure to be here. And it's a little bit unreal to think that we can look back a full 50 years. One would never have thought that this would have such a big impact. As Charlie said, not only were we interested in directly logging into remote computers, but there was a kind of bigger vision that the computers might work together on a problem, or that there might be other kinds of applications. So a number of us tried to think about the general case of how do you build protocols and share these protocols across all the different machines. And most particularly, we understood that we were not going to get everything right all at once, that there would be ideas that would emerge later, and it was important to leave room to build on top of whatever we thought about. So we gravitated toward an open framework that you could have a base set of protocols, but then on top of that, you could add other applications. And so things like Skype and HTTP, the World Wide Web and so forth, were in a general way part of the vision that we had without knowing exact details of how all of those were going to emerge. So as Len has described and as Charlie has described, we formed a network working group of people who were our counterparts at all of the different hosts, starting with the first 4 hosts that were designated for the initial network and then expanding as the network expanded, and developed both the social framework for us to work together and the technical framework for building the protocols. It seemed, in a way, straightforward. I had other research ideas in mind, and I didn't think that this was as intellectually compelling as the other ideas I wanted to pursue. I was wrong. This turns out to be pretty interesting stuff, even from a research point of view, as well as the obvious practical benefits. And then a short time later, in this, when we look at a 50-year span, it became evident that we need to connect other networks together for multiple reasons, internationally, different technologies, different agencies and so forth. And that led to the birth of the internet, and here we are today.
It's absolutely fascinating to listen to these stories. The first thing that comes to my mind is, after those initial messages, what were the next steps? What did you do next? What was the plan? Was there a plan actually?
Yeah, that's the right question. Most interesting. So Len described the set of advisors and working with Larry Roberts on a plan, and that both Brannick and Newman had won the contract from a formal bidding process. So the hardware part, the switches, the long distance lines that were procured from AT&T, all of that was a well organized plan that had a budget and had a schedule and was managed quite carefully. The part that I've described about trying to design these protocols was not at the top of the list of things that were planned carefully, and it was more a question of, well, we'll let the users figure it out, sort of a field of dreams almost. And of course, it was obvious that the network would be used for at least two things: the logging in machines, as you've heard, but also moving a file from one machine to another. But the more advanced types of applications were not thought very deeply about and were not part of a careful plan. And as I say, that emerged during the process. So that, I think, is a quite remarkable situation, because in leaving room for building more things, it worked out exactly as expected. That is, ideas came from every place. Different people made applications. There were early experiments with speech. There were early experiments with graphics over the ARPANET. It took a long time, of course, before the hardware that we're using today emerged in a cost-effective fashion that everybody could use. But the basic vision of these things was clear enough even at the time.
There was another aspect to it, if I may.
Yes, of course.
So Steve is properly describing the use of the network and the structure to allow that use. But beneath it all was the engine, the infrastructure, the network. And we were tasked to make sure that that underlying structure was working properly. So as I mentioned earlier, our job was to try to test the network, to stress it, to try to break it, and find out if there were errors that needed to be fixed. And so after the first two nodes, we got a third node in November and a fourth node in October. And we tested that 4-node network for a number of months, trying to break it. We could break it. We could cause deadlocks and degradations and inefficiencies. We found out some of the underlying issues, recommended how to fix it. They got fixed. We found others. There were a large number of software and hardware errors in the underlying infrastructure that we kept probing to make sure that these faults were found, fixed, and not occurring again. So there were basically two aspects. One was making sure the engine was working, and Steve and his group were making sure that the applications were able to be accessed and to come up. So it's a rather interesting parallel effort. We had basically different groups working on it. We had my PhD students at the theoretical end, looking at the analysis, the experimentation, the optimization, the principles. And Steve, who was in charge of the software group, he hadn't mentioned that. Hats off to you, Steve. You were basically pursuing those other aspects of using the network and setting up the protocol to allow that use.
Charlie, do you want to add something?
Who did he say?
If you want to add something to this question.
There were a number of interesting stories from that time. Hello?
Yep.
Oh, okay. I hear you. I just don't see me, but that's all right. There's a number of interesting stories. For example, during the bidding process, AT&T and IBM refused to bid. One of them didn't think it would work, and the other one wanted to use a different technology. They wanted to use circuit switching rather than packet switching, which wouldn't have worked at all. There were difficulties in trying to cobble together the 50 kilobit lines, which were done by taking a bunch of 4800 baud lines with a special modem that made them work together to create the 50 kilobit circuits that were used. BBNN had some interesting examples of strangenesses when there were always two lines to each site, at least in those initial sites, to try to get redundancy. So we had a line from UCLA to UC Santa Barbara and a line from UCLA to Stanford Research Institute. And they seemed to go down at the same time. It turned out AT&T was multiplexing both lines on the same physical circuit on different frequencies. And so when that line failed, both lines, the redundancy wasn't really there. And BBNN discovered that there were certain circuits that seemed to go out at strange times of the night, like it'd be down from 12 o'clock to 12:02 or whatever. And they called up AT&T long lines and said, this circuit, and they gave some big long number, was down from 12 o'clock to 12:02 on the following day. We want a refund. And AT&T's comment was, how can you know that? We can't know that.
Charlie, why don't you describe the headphone you were using to derive the voice line for your communication with Bill?
On the same circuit that the data was on, there was also a voice line, which was really there for the purposes of troubleshooting for the AT&T engineers. And so there was a headphone connected to the modem as well as the computer. We had this. It was like an old operator headphone that you stuck over your head, had a little thing that went down in front of your mouth and a little earpiece. And it happened to have a very long cord. So it was convenient to have that on when I was trying to do things with, say, for example, Bill Duvall at SRI, because I could sit at the terminal and have both my hands free and be talking to Bill. So we were using this weird headphone at the time. At least I was on one of the occasions. On the occasion of October 29th, I think we were actually using a regular landline. I don't remember 100%. Neither did Bill. I asked him the other day, and he couldn't remember either.
Let me offer another little story. So 50 years ago was 1969, and the network continued to grow what seemed like a very fast pace of putting in roughly one new IMP. Hosts were connected to that. Sometimes just one host, but occasionally there were two or even three hosts at a site. 2 years later, in 1971, I took a break from my graduate studies and went to Washington to work directly for Larry Roberts at ARPA. And the first thing he asked me to do was to go down and consult with an Air Force group that was going to connect their computers to the network in order to do a side-by-side test of moving files across the ARPANET versus moving files across what was called AutoDIN, the official U.S. Department of Defense network. So I went down and I consulted with them, and I suggested that for this particular purpose, to make it good, they should try to move send as much data as possible. And I suggested to them that they could set up parallel connections. Instead of just sending a message and waiting for a response, they could set up, let's say, 8 parallel connections and then assemble the results afterwards. What was not clear to me at the time was that this would cause a flood inside the network. When they finally got their software working several months later, the network went down. And when I say the network went down, I'm talking about the entire network across the United States, and it died within 4 seconds. Now, these poor guys, very competent people, Air Force officers, who themselves were graduate students, it turned out, in a nearby university, they couldn't tell what was going on because nothing happened. Meanwhile, up in Cambridge, near Boston, the folks at Bolt, Brannick, and Newman saw the network go dark and started to work feverishly to bring it back up. And they had to work with one host, one imp after another. And while they're working on it, these guys down in Texas, in Oklahoma, is where the Air Force Base was, said, I don't know, let's try it again. 4 seconds later, the entire network crashes. Eventually, they discovered each other and brought the network back up. And in the course of that conversation, they said, well, Crocker told us to do that. Crocker at that time was sitting in a meeting in a closed room at MIT and on a different topic. And somebody came in and tapped my shoulder and said, there's a phone call for you. So I got on the phone and there was somebody from BBN yelling at me. And he didn't even say who he was, although I could figure out who he was. And he accused me of doing it on purpose. And I said, no, not really. At that point, I was a government employee. And I said, you know, this really is more my network than it is yours. I wouldn't do this on purpose. And but it was a learning experience, as we say. And adjustments were made and that problem went away. But as Len talked about, so that's one example of the kind of thing that Len was describing, of learning about the dynamics of the underlying machinery and how to deal with that. Fortunately, today that doesn't happen. There's enough resiliency and enough controls inside the network so that the whole network doesn't crash all at once.
So there was some interesting crashes, though. While on that subject, Steve, you opened up a lovely Pandora's box of stories. There was one time when the Harvard switch claimed it had 0 delay paths to every other node in the network. That was a software. And so all the traffic in the network found its way to Harvard. And every time Harvard sent it back out, it came right back to Harvard. So finally, the Harvard imp crashed and the network came down. But there were some other interesting stories. For example, the very first line from UCLA to SRI, that link was in there, and you can see the evolving topology. It remains there until April of 1972, and that link is gone. And, you know, you can be a hero by adding more links to a network. But if you remove a link and the network fails, you're no longer a hero. So it took some careful topological design technology to be able to design the topologies as we run along. And the argument is you can't design a topology on the back of an envelope. It's far too difficult. Well, the fact is, by November of 1972, the network looked like the back of an envelope, which is a kind of ironic, interesting story. Another case where the network went down is one day they doubled the storage in the switch, the hardware storage, and the network went down. And that's a longer story, but just by adding capability, that caused another kind of failure in the network, and down it went. It was a software bug, but they were wonderful. We could go on and on telling you about the kinds of failures that occurred. But each time we found them, we fixed them, and it never happened again for that reason.
Yeah, sure. Go ahead, Charlie.
I was going to say that while the network as a whole doesn't go down anymore, routing errors or other errors cause major parts of the network. Gmail, for example, has gone down on several occasions because of some configuration error at Google, and similar stories. So the network itself doesn't go down, but important parts have sometimes had problems.
I couldn't help myself thinking about that. Those kinds of routing errors, we seem to be having those these days still, like, advertising paths that are not there. I've heard that before.
Werner Herzog interviewed me for his documentary, and he asked me, can the network go down totally? And I said, no, there's too much redundancy. It's awfully hard to do. And then he came up with a wonderful comment. He said, what if there was an enormous solar flash from the sun? That would take the network down. It would take you and me down as well.
Yeah. So Those are some wonderful stories, guys. I have a sort of a very, very short personal story. My first IETF meeting was the IETF 66 in Dallas, Texas, which is famous because it was the IETF of the flood. I remember standing in a hotel lobby, and there was a floating wooden elephant right beside me at some point. Yeah. And one of those nights at the hotel bar, I remember overhearing stories about the TCP/IP migration and how people even made T-shirts saying that, "Wait, I survived the migration." So we've probably been waiting all these years to have the opportunity to ask you guys about how was that migration? Was it indeed that terrible?
It was fundamentally slow, approaching that date, but the network did not come down. It was decreed, and it happened.
Of course, different sites took different times to adjust. At UCLA, it was actually fairly easy for us because by that time we were running Berkeley Unix, which already implemented TCP/IP, so we didn't really have to do anything other than switch to TCP/IP. But other sites had to do a lot of work implementing TCP/IP and switching their applications to use it.
Steve?
I was not part of that transition process because I had turned my attention during that period to other matters. But as a more general comment, you heard earlier Charlie say everybody had to build their own hardware interface, for example. And then you just heard Charlie mention that later UCLA was running Berkeley Unix. So there was an evolution from the very earliest days from one at a time implementations of both hardware and software to replication so that you could share the results. First, the results were shared between laboratories, and then in relatively short order, there were products. You could buy a hardware interface for a PDP-11 from DEC, from Digital Equipment Corporation. They sold it as a special product, but you could order it. And then over a period of time, there were companies that would make hardware interfaces, companies that would make the software, and then eventually, as we have now today, it's all built in and nobody has to think very much about it. But that was an evolutionary period. It took place over several years. One very important part, which has affected everybody, is the small scale. How do you connect a bunch of computers within a relatively small area? It's the so-called local area network issue. And there was a period where there were a lot of competing technologies, ring networks and other kinds of things. And the one that emerged as the winner was the Ethernet, which Bob Metcalf and his team at Xerox PARC had put together, using some ideas that came out of the Aloha project at Hawaii, which used radio communications between a central computer and a bunch of terminals. And then with that experimentation of developing the Ethernet, Sun Microsystems put Ethernet interfaces into all of its computers and made that the standard. And the world changed at that point. Nowadays, it's hard to imagine buying a computer that you can't just connect to everything else.
You know, talking about CSMA, Abramson came to a meeting one time proposing a thing like CSMA, and I was there with one of my students, Fuad Tobaji. And on the plane home, we looked at the equation he put on the board, and he said, "No, that's not right." So we looked at it, we corrected it, and that became a PhD dissertation for Fuad. And Fuad actually coined the term carrier sense multiple access.
Is that right?
Yeah.
The other side of that is Abramson had come. I was working at ARPA, and Abramson came into the office, and I had not been paying attention to the AlohaNet, but I was talking with him, and he's describing it. And I was quite impressed with the idea that you just have these terminals send whenever they want and use the acknowledgement process to sort out collisions. And I took home the proceedings that we had in the office that had his paper in there, and I had it came and visited me and stayed on my sofa bed. And I said, this is an interesting paper. You might find this interesting. So he read that paper, and he too got annoyed with the mathematics of it, and went home back to Xerox PARC where he was working, and took the ideas, put them in a cable, and there we have the Ethernet. So I have had the singular pleasure and distinction of being the host of the father of the Ethernet.
By the way, one other point, talking about the IMPs, the switches that BBN put together. The idea, which simplified Charlie's life and Steve's life and my life, was to create a special switch. We now call them routers. We call them IMPs or packet switches then, separate from the host computer. The idea was to take all the communications functionality out of the host and not burden it with all that complexity, and put it all in a dedicated machine. We now call them routers. That greatly simplified the design of the network and the kinds of interfaces that we had to create. Instead of doing truly major surgery in the operating system, we did minor surgery, as Charlie and Steve described, to allow us to talk to the network. And that was true for every other site on the network. By the way, the gentleman who suggested that separation is Wes Clark out of Lincoln Laboratory.
And that's an absolutely crucial point, Len, and I'm glad you included it. And I think since we're here 50 years later, it's important, I think, also to understand the technology situation at the time. It was a period when computers were generally very expensive, and they were large and they were bulky. And Wes Clark was very interested in small computers and had a lot of experience with what you could put into a small computer and make it cost effective to have as essentially an early version of a personal computer for laboratory use. So that decision to aggregate the switching process in a separate computer was rather extraordinary and revolutionary, in the sense of you mean we're going to buy a new computer for every site? That would not have been financially sensible even a couple of years earlier. And of course now you can't count the number of computers in your pocket, much less the ones in your laboratory. But it's a Moore's law effect. It was the very rapid decrease in cost of computation, the very rapid increase in the amount that you could do for a given dollar, that made that decision just barely feasible. Those routers, these IMPs that we're talking about, were $100,000 US dollars in 1969 dollars. So that'd be like $500,000 or more now. You go into a store and you buy a router and it's got Wi-Fi and everything built into it for $25 or less.
You know, Steve, you raise another interesting point. You mentioned Moore's law had to come in to allow some of this to happen. The fact is, the idea of what we now call an internet was in the minds of visionaries more than 100 years before the ARPANET, more than 100 years from now, 50 years before the ARPANET came in. There were visions of what this could be, and they are articulated in writing. The fact is, as you say, the technology had to catch up to the vision. And when technology came, then in fact it could be implemented, and the ARPANET, hence the internet, was the manifestation of that technology development.
I have a question from the audience, which is, I guess, comes from Venezuela, Alexis from Venezuela, and I think this is something we all want to hear from you guys. Is how do you picture, how do you see the next 50 years of the internet? What are the next innovations you think may have an impact on the internet? Let's say, I don't know, artificial intelligence, Internet of Things, I don't know.
So you're asking two questions, or she is. She's asking about the underlying infrastructure, and she's asking about the applications.
Exactly.
And as I've said many times, the infrastructure is far easier to imagine. You mentioned one important component, the Internet of Things. I believe that, as I said back in 1969, this network will eventually become invisible. It will disappear into the infrastructure. You won't have complicated devices you have to play with, but you will be able to talk to a room, a space, wherever you are, and converse with a thing called the internet using language, haptics, gestures, even brain internet interfaces, which are now being developed. And you won't see it. It'll be as easy to use as electricity is. It's a plug in the wall. You don't see it. You plug in easily and you get the service. You don't care how it's made. So the way to basically unwind that is to, in my mind, we will see a pervasive global nervous system across the planet called the internet or some other name, but that same functionality. But the applications, on the other hand, the only thing we can predict is that we will be unable to predict the applications. We have been surprised over and over again with explosive, sudden applications that dominated the internet that we didn't see coming. First example was email, then YouTube, then Instagram, then social networks, then peer-to-peer, then search, on and on and on. So it is going to be an unpredictable, wonderful, surprising technology which will allow the youth of today and tomorrow to continue to contribute. That's my soapbox.
And there are some serious technological challenges. For example, when there's only a few people writing applications, you can, if there's a bug, you can fix them. But when you have Internet of Things and millions of devices, and a bug occurs which allows them to be controlled and suddenly remotely by someone nefarious actor, and suddenly they can take this network of devices and do bad things. So we have some serious technological challenges on the security and the privacy of those devices. You know, I want to be able to have the camera in my house and the Google Home and all these other things, the Alexa, but I want to make sure that it's secure. And there's some real tough problems.
You know, I'll give you an interesting example that occurred to me just yesterday. I was going to wire some money to a company for an investment purpose, and they had sent me the wiring instructions. And before I sent it, a few hours before, I received another email which says, uh-oh, that was the incorrect wiring instructions. Here's the correct ones. Steve is smiling. And sure enough, was a fraud. Now, it seemed to come from the right source. If I hadn't been suspicious about some aspects of that wiring instruction, I would have lost my money immediately. So you're right, Charlie. There are nefarious actors out there who are looking to do harm.
You want to send $1 first and see if it gets there.
Oh, you've been there, Steve.
No, but it's possible to lose money in many, many ways. Len's gave my speech. I mean, if you'd asked me first, I would have said the internet's going to disappear from view. It's going to be everywhere. And you'll stop asking when you go somewhere, is there an internet connection? Just like you don't usually ask if there's electricity in most parts of the world that we deal with. But as Charlie said, there will be some challenges on security. There'll be challenges. Security is a very big topic that has got a lot of different aspects that don't all have a single solution. So you have the problems of whether or not have bugs in them or whether they're sort of airtight. And then you have the social effects about misuse of data or surveillance and so forth. Impossible to say how it's all going to work out. The social aspects not only include obviously improper use, but as everybody is now seeing, you have values that vary in different parts of the world. So different countries have different ethics about free speech and about the role of the government versus individual behavior. And because the network now connects us all across the globe, these differences now come into conflict with each other. There's no obvious solution that is going to be simple. This is going to be a pretty bumpy ride for a while.
Excellent. I have now a few questions from the audience. I think it will be interesting to spend these last 10 to 15 minutes with some questions from the audience. I'm going through the list. I'm going to start with one that I'm going to join two questions in one because I think they are more or less related. How do you think the implementation of 5G, of the fifth generation mobile network, will affect the internet, if in any way? And how do you believe that the fact that now video is the leading application on the internet will affect how the network scales in the future?
So if I'll jump in, 5G is just another step toward the invisibility of the network, where you'll have excellent access in many areas, not everywhere. So the bandwidth will become less of a problem. But the use of this network will continue to be a challenge. The infrastructure, I have no question, continues to improve. 5G is just one example.
Charlie, Steve?
I didn't say, go ahead, Charlie.
I was going to say, one of the problems with 5G is that while it increases the speed dramatically, it doesn't travel very far. So you suddenly need zillions of little access points, where a regular cell tower today can go a mile or two. The 5G access points go a few hundred or 1,000 yards. So they have to put these little access points all over the place, which also has whole issues of the backhaul to the main network. And it's going to be a real complicated deployment. But as Len said, it's just another underlying transmission technology which will increase speed and access as it's finally deployed.
There was a second part to your question that I didn't quite hear. In addition.
Yeah, how do you believe, guys, that now that the video is the leading application on the internet, how does that affect how the network scales in the future?
Yes. Well, that's a very interesting thing, because we've lived through a period when the main communications was ASCII, without any fancy fonts or anything, and then we got fancier and fancier fonts, and then we got graphics, and then now eventually we have video and voice, of course. I've been humorously describing that I've been working on this network for technology for 50 years, and I didn't understand what it was all about. Now I do. My wife spends all her time FaceTime with the grandchildren, and that is, from her point of view, what the internet is all about: FaceTime with grandma. There's another aspect besides 5G that is going to be pretty interesting. We're already seeing a little bit of it. You're going to see a great deal more, I think, that will very positively affect Latin America, and that is low Earth orbit satellites. It takes a long time to get up to a geosynchronous orbit, and it's a quarter second up and down, and half a second round trip. When you have low Earth orbits, it becomes feasible to have essentially real-time communications, and you can reach the rural areas, the mountainous areas, in a way that is very hard to do over landlines. So I think that they will play a big role in reaching the second half of the population. We have about half of the world's population connected now, and look at how to reach the rest of the world. I think that will play an important role.
That's a great point, Steve. But the streaming concept is rather interesting. I have two comments about that. The first is, we can thank a lot of the ability to do streaming traffic to a researcher named Danny Cohn, who many years ago asked that TCP be separated into TCP and IP, so that you could run UDP on top of IP, which allows streaming traffic to go through without the overhead and the correctness and the packets in order that TCP tends to require. So the capability was laid long time ago in the late 70s to provide for streaming capability. The second point is that since streaming traffic is becoming such a large component of the internet traffic, it does open up the possibility for another kind of architecture. Charlie mentioned circuit switching before. Circuit switching was woefully inadequate, as I said, for handling computer-to-computer communications. But it turns out that with technology improving, one can introduce something called fast circuit switching, where you set up a bandwidth, a pipe, you stream some traffic, and you let go when you're done quickly because the capability is there these days. And if we go to a fast circuit switching kind of system, we get another advantage because circuit switching is a kind of space-time allocation of bandwidth, which means that one could send data through a network without carrying the source and destination address. It's all determined by where you are and when you're there to determine what the rest of your path is. That's a kind of, as I say, a space-time allocation. If that were the case, if we could send data without source and destination address, that adds a great deal of security to the traffic, because if you start capturing traffic or sniffing it, a few bytes come by, you don't know where they came from, where they're going for, they may or may not be encrypted. It's not that useful as it is now when I can tell where it's coming from, where it's going to. So it's opening up the potential for new architectures, certainly in greenfield cases where there's no internet yet, to be designed in such a fashion. But that's a research subject.
That's an excellent point. And let me add just one little technical comment. The original focus on packet switching was to make use of the bandwidth in a very efficient way. What turned out very quickly was that you needed space in the routers, in the switches for the buffers. And the original switches had very, very little space. It's been very, very important that memory has become cheap and that you can have enough memory so that you can have the way of routing these things and doing the very fast switching that Len has described.
Thank you, guys. For a minute, you brought that nightmares of something called ATM, which I'm sure you all remember.
ATM and frame relay and so forth are all various aspects of exploring that trade-off between addressing and pre-allocation of space and pre-allocation of on the circuits and so forth.
Yeah, I kind of liked ATM, but when I started liking it, it died. So, so I have two more questions. Wilfrido from Ecuador has a question that I think is very interesting, and let me translate that into English. Can you tell us a little bit about how you guys started working on technical coordination? I would say, I would say the early days of the ATF. Coordination on numbering and naming, you know, the kind of coordination that eventually gave birth to organizations like LACNIC.
Steve, that's yours.
Yeah, I could see it coming. The early discussions were these protocols and how to get the software working, and there was not very much attention to formality and structure and governance and so forth. But over a period of time, it became clear as things scaled up that there needed to be a little bit of attention to that. So it emerged in several different ways. We had these meetings that the network working group, those meetings over a period of time went through several changes and became the Internet Engineering Task Force. We designed these protocols in an informal way, and we did not have a acceptance process or a governance, that said this is formal. But over a period of time, it was desired to be able to declare that the work had been done and that this was now a standard. And and we published through these documents we called requests for comments. Nowadays, by the time a document, a protocol is specified in a request for comments, no more comments are required at all or requested because there's been all this work beforehand. It's been interesting to compare how all that emerged compared to the usual standards processes. We don't have a formal conformance process. Sort of the marketplace determines it. You develop an implementation, and if it doesn't work with everybody else's, then it doesn't be says that it's the right implementation. And then, as you alluded to, the names and the numbers started to become important. So in the early days, it was very simple: 1, 2, 3, 4. You know, assign the next number. The addresses started to get complicated. And eventually, organizations like LACNIC had to be created to manage the address space. It would have been impossible to imagine that we would need such a thing in the very earliest days. And it's the kind of thing that comes, I guess we call it a success disaster. Things grow so big that you now have a problem. It's a nice problem to have, but it's nonetheless a problem. And on the naming side, who would have ever thought that we'd have to create an organization like ICANN that consumes $140 million a year or so just to coordinate the top level of the address of the namespace. These things are sort of evidence of the success and artifacts or maybe they're just the necessary baggage if you take a negative view.
Thank you.
I remember in the early days of TCP/IP when DNS was beginning to happen, and they created the .coms, .edu, .org, and our friend John Postel was effectively the czar of the names and could make the decisions whether a given group could have a particular name. And there were actually a team of lawyers that were constantly defending him against lawsuits because somebody would say, I want that name, and somebody else would say, no, that's our company name. You can't have that name. You can't have IBM.com. And there were lawsuits that he was being defended against.
I can imagine. So I would like to move to one last question, which comes from El Salvador, which I think it's also an interesting question. Charlie made a few comments on this before. Leo from El Salvador mentions that he can actually see how you guys were able to improve your software, but he is sort of mystified, I would say, how you guys were able to bridge that hardware gap you have. The fact that there was simply no routers or interfaces or anything you could go out there and buy. How did you manage that?
Well, at least at UCLA, we had a smart engineer. It started with Bolporanic and Newman wrote a spec, and they knew they had to interface to lots of different kind of computers. So they came up with a very simple 4-wire protocol, which they specified. Here's the voltage. Here's the signal where the wire where you put the data bit on. Here's the wire where you say, I've got a bit on that wire. And here's the wire where you say, okay, I've taken the bit. You can repeat the process. And it was such a simple protocol that it was relatively easy to see how you might design hardware to implement to it, and also so each site had to, figure out how you integrated to the buses or whatever of your particular computer and implement this particular hardware. We had a very bright guy at UCLA, Mike Wingfield, who was able to use the hardware lab we had and build that interface. Some of the other some of the other sites went out and contracted somebody to build their interfaces for them. For the cases where the same computer was used multiple times, then once the first one was built, then other sites could have a copy of that same interface built for them. So we just managed through it.
I had an opportunity to talk with Mike Wingfield a few days ago, Charlie, because you connected me up with him. I appreciated that. And he pointed out something that I had not realized before, but for his master's thesis, he had worked out the hardware interface for a display, for a graphics display
to the Sigma 7. And so he was already familiar with the, and he was able to make use of that in designing the interface to the IMP.
So I think with this last question, this brings us to the end of our webinar. I would really, really want to thank you, all you guys in the name of LACNIC and all of us here in Montevideo. It was an amazing hour. And I, again, thank you for the time and thank you for being here during these past few days doing audio tests and everything. We genuinely appreciate that. Thank you very much, guys.
Well, congratulations, and it's a pleasure to have been with you.
Yeah, it's been a pleasure to join you today on the conversation.
Good questions, good discussion, and a wonderful organization. Thank you.
Thank you all. Now over to Maria, who will have some final comments.
Thank you all for being here and participating with us. We are really happy to have this webinar today. And we just wanted to add that this webinar is framed in our LACNIC webinars program that we have every month. We have like 1 or 2 webinars per month. We invite you all to join us. We have some webinars in English, other ones in Spanish. And some people always ask about the recording of this webinar. We will publish it in the website that you are watching the streaming right now, so we'll have it tomorrow in English and Spanish. And thank you all for joining us, and thank you to all the pioneers that have joined us today, and talk to you soon. Bye.